Hello, everyone. We're just going to let everyone join, and then we're going to get started. Okay, as people start to file in, I'll get started so that we can stick to our time schedule here. Good morning, everyone, and welcome to Demo Day for the U.S. Department of Energy's Digitizing Utilities Prize Round 2. We're thrilled to have you join us today to witness the exciting progress that's been made.
I'm not sure if.
Fernando, I think if you could mute. Um, We're thrilled to have you join us today to witness the exciting progress that's been made by these talented teams competing in this prize. A few housekeeping items that I'd like to go over. One, this is being recorded, so for future viewing, but also for you all to know that this is being recorded. If anyone has any questions that should go in the Q&A chat, please. We will do our best to facilitate them if there is time after the judges have addressed their questions. And then and then also please follow the Round 2 Hero X page for more updates on Round 3 funding opportunities and the notice of intent that we have published for that prize. And later, Carly will be dropping that link in the chat. Okay, so following a successful round 1, this year's competition has brought together interdisciplinary teams of software developers, data experts, and utilities to tackle some of the most pressing challenges in the energy sector. With support from the DOE's Office of Electricity and the Office of Cybersecurity, Energy Security, and Emergency Response, the $2.15 million Digitizing Utilities Prize is helping to accelerate the digital transformation of the U.S. energy infrastructure. As we all know, the electricity sector is facing an explosion of data streaming in from a variety of sources such as sensors, weather systems, and energy use patterns. This surge of information presents both an incredible opportunity and a major challenge for utilities. Traditional methods of data acquisition, processing, and storage are being tested like never before, and the sector must adapt to effectively manage and harness this influx to ensure a reliable, resilient, and sustainable energy system. In round 2 of the Digitizing Utilities Prize, the focus has been on developing innovative solutions to enhance data analytics and the digitization for utilities. These solutions span a wide array of topics, from addressing data quality and interoperability to improving data systems to cyber attacks to integrating diverse data sets for better operational decision making. This round also shines a spotlight on cybersecurity, with competitors working to protect critical infrastructure against evolving threats. Throughout the next 4 hours, you will hear from the teams who have been working side by side with their utility partners to address these challenges. Over the past 4 months, these teams have refined their solutions, and today they will share their progress, demonstrating how their work is making a meaningful impact in real-world applications. Each team will have 10 minutes to present their challenge, their concept, and their solution they've developed. We'll get to see a few teams give impactful demonstrations, and we will hear them discuss the integration of their solution into the utility's operations and highlight the potential impact, not just for the partner utility, but for the industry at large. You'll hear about advancements in everything from data analytics to cybersecurity to disaster resilience and more. Each presentation will have a 10-minute Q&A session with the expert reviewers after. Before we dive into the presentation, I'd like to take a moment to thank all of the teams for their hard work and dedication, as well as the U.S. Department of Energy for making this initiative possible. We're excited to see how the solutions presented today will help shape the future of energy systems across the nation. And so without further ado, let's kick off today's demo day and see how these teams are transforming the energy landscape and their innovative approaches to data and cybersecurity. Enjoy the presentation, and let's celebrate the incredible potential of digital solutions to power the future of our energy infrastructure. And before we get to the presentations, I'd like to hand it off to Sandy Jenkins from the U.S. Department of Energy, Office of Electricity, for a few words before we start.
Great, thanks, Alec. So I am Sandra Jenkins. I'm in the Office of Electricity and the Director of Grid Controls. Within the Office of Electricity, we focus on reliability, resilience, security, and affordability of our nation's power grid, and developing research and technologies and demonstrations for improving those things. Through data analytics and digital technologies, this prize aims to support partnerships between interdisciplinary teams and utilities, as Alec so greatly summarized. We're excited about our first demo day for the Digitizing Utilities Prize, and thank you for NREL for hosting this, and for all of our judges. And thank you for the teams and their demo partners for their participation. And finally, thanks to all the attendants for other folks who have joined the call today. Alec, back to you.
Great, thank you, Sandy. And I will now show the presentation order and hand it off to Carly, and we will get started with the first presentations.
Yeah, thanks so much. We're excited to have everybody here. Just as a reminder, you will have 10 minutes to do your presentation. So I'll have a stopwatch over here, and then I will throw in the chat when you have about 1 minute left. So you could be just keeping an eye on that. And then we'll transition into the Q&A session. We'll have another 10 minutes there, and then we'll transition into the next team. So if you're the next team presenting, just be looking. You will get bumped from an attendee to a panelist, but try to make sure that when you join, your camera and your microphone are off so that we're not interrupting anybody ahead of us. But we should have Luke and Zach already as panelists here. So whenever they're ready, I believe Zach will be sharing his screen for the presentation. And he might just take over that permission from you, Alec. But as soon as you guys are ready, I will start your 10 minutes.
All right, and I'm trying to press share, Carly, and it's saying I can't while the other participant, there we go. All right, everyone, can you see my screen okay?
Yes, we can.
All right, let's start the timer. Quick intros. Hey, everyone, I'm Zach Kanders, one of the partners of Chain SCADA. My background is in software development for the utility industry. About 20 years experience focuses just on that area. And I'm joined today with Stephen down at Hingham Municipal Plant. And in the background, you can see they got their solar car top charger thing behind, which is pretty cool. So, well, Stephen.
This has been an exciting process. My name is Stephen Girardi. I'm the engineering manager for the Hingham Municipal Light Plant. We're located just south of Boston. We serve 11,000 electric meters. We have 150 miles of overhead wire, 100 miles of underground. We're a growing load, and we're very into the transitioning from fossil fuels into new reliable green energy. So introducing the chain SCADA, the main objective is how can we manage our data outside of our organization in a secure fashion? And one of the things we've been looking to do is to work with other, members or developers to help them easily access our data without taking time away from us from doing so. So this is where Chain SCADA came in to give us a help.
And what's kind of fun about this whole project, those photos, that's a real SCADA environment down here in Hingham. And, if you follow just the industry trends, like a lot of the vendors in the community, they got this saying, they'll say, SCADA, it's where good data goes to die, right? So part of the exploration, like Stephen said, is let's find a way to democratize, let's get the information out, let's make it interoperable, let's align it with the goals of electrification, renewables, energy transition. at the end of the day, right, energy is going two ways now. Let's get deeper into the feeders, understand the devices, and then make it shareable. The other key piece of data is that, SCADA really hasn't, excuse me, the DMP3 protocol, which is really what is the backbone for SCADA, hasn't been touched since the 70s, in terms of total revolution, right? Like a transformative approach. Now, I know on the call today, there's going to be a lot of folks talking about data, AI, how do we do time series analysis different and new? What our team sought out to do is transformation, right? How could we embrace some other technologies and capabilities to do something really unique? The key other piece is that SCADA is growing, right? They're predicting this thing to basically double in its market the next 10 years, just based on all these assets that are going out.
So understand the problem, the security vulnerabilities, limited interoperabilities and compliance challenges. All this affects all the utilities, and how can we share the data in a secure environment?
Picture on the right, we had to show code somewhere, right? So we actually wrote code to do this. It took some research, and we'll go a little bit deeper, I'm sure, in the Q&A, but we really set out to say, hey, if you were going to put energy data, operational data, SCADA data onto a blockchain, what's the right framework to do it? There's obviously been a lot of PhD discussion around the topic, but a lot of it focused on, transactional uses, settlement, things like that. So we focused on something called the Hyperledger Fabric, which is part of the Linux Foundation to enable true peer-to-peer, business-to-business shareability of information.
So the primary objective for us was to have it a secure, different data logging, and again, to be able to share data with others and actually try to capture some grid anomalies in a secure fashion.
Who we're targeting. So this goes well beyond utilities, right? Think about the critical infrastructure environment in the US today. There's a lot of different sectors that rely on each other to be able to coexist. Maslow hierarchy needs, water, food, shelter, electricity, gas, water. I mean, the whole thing's now interconnected. You take that with Moore's law, the amount of compute happening on a chip, and it gets real obvious that there's a lot of people that need this key information during really big events. So a lot of what we focused on was who are the key ones, right? So we said it's the utilities, the local utilities, it's the regulatory environment, and now it's becoming the distributed energy resource operators, right? The solar panel providers, the battery providers that want to coexist in here. And then also public safety. When the power goes out, it's not just the utility working on getting the outage on, it's the police department trying to manage streetlights and things like that. How can we open up the SCADA databases to be able to get everyone informed in real time?
So as the project we started, when we first met with Chain SCADA, we had the idea and we brought it to a point where it's the proof of concept. And just by Zach showing the code, this is kind of where we're at right now with this. And it's been exciting times for us. And this provides a lot of opportunity for future enhancement because, as we move forward, we're looking to get into a smart grid, self-healing grid, and all this data that can be collected in secured paths between us or consultants or the DER owners. It helps us reduce our time trying to collect that data while other people can grab it for us and start studying. So on the next going forward.
Yeah, what we're thinking there is we need help from the Department of Energy and also NREL. We did talk to the Open ADMS test team at NREL. Said, hey, if we do progress into this next phase, really would appreciate you testing the code that's been created, further expanding upon these concepts of smart contracts, which we'll cover in a secondary slide, and then also soliciting groups like an ISO or an RTO to be able to help them embrace and visualize data in a new mechanism. So we really are calling on the help of a couple different entities to help this thing grow and expand from where it is. Luke is on the call. Luke's on a cruise ship today, everybody. So Luke, are you able to cover technology?
It should be great. Yeah. So this diagram provides a high-level view of how Chain SCADA integrates with traditional SCADA systems and also leverages blockchain technology. On the left, we see the existing SCADA infrastructure where field devices communicate with master devices via the DMP3 protocol. We saw this as an opportunity to tap into that communication layer. So this data is replicated to a demilitarized zone read-only for added security. And then at this point, Chain SCADA has a virtual master device daemon that processes telemetry data without interfering with the existing operational SCADA system. So this data is replicated to, these readings are replicated to our master node and then communicated out over to our main platform in AWS, Amazon Web Services. This architecture includes key blockchain components like peer nodes, ledgers, and smart contracts. These smart contracts run business logic on transactional changes like frequency variations and readings. Based on these smart contracts, they're able to send readings to an anomaly detection service that can detect fluctuations and variations and issues, and then from there notify critical stakeholders through SMS, email, voice, and push notifications, some still to be created.
Luke, just playing off what you just said, we tested it, right? Real operational environment. The interesting one, we did this for the Department of Energy frequency, right? As the amount of generation in the fleet starts to go down, as you see growth in solar, that spinning reserve and then the susceptibility to voltage highs and lows are obviously going to become a major impact to grid operators. So we looked at, sorry, I said I combined voltage frequency. The next one's voltage. Frequency anomalies, right, with the spinning reserve impact, because you're going to have just a solid state like a solar panel on and off type environment. Those sensitivities are going to be growing more and more, especially when you have spinning equipment at a factory. So we looked at setting rules around frequency, right? If you had anomalies on the frequency, being able to detect and notify in real time to someone like an ISO, and then more so with like a voltage component. Tested this one in the field. If you have a sag or swell on the voltage falling outside the nominal, being able to see that in real time, both at the utility, but also at the plant operator or at the DER. And Steven, if you want to cover a quick example of this one.
Yeah, so actually about 2 weeks ago that there was a transient along the transmission system, and I happen to let Luke and Zach know is we had multiple customers call throughout the system and say, hey, their lights went out and came back on. So everything was all normal and operational at our stations. I had to go back into our SCADA system and go through previous data intervals from and just see where the dip was. And the customers actually all saw a quick 500-volt dip over like five cycles. We were able to capture that on our SCADA system, but having to be, it would be very nice at that moment that I know that we had a drop in voltage in during that particular time, because it took about 30 minutes just to figure out what happened. So as an example, this would have been extremely useful for us.
We talked about next steps. You know, we're looking for feedback, testing, refinement, and honestly more smart contracts, not just the frequency smart contract, but voltage and other use cases to help the other critical infrastructure providers or utility data sharing. And that's hopefully our 10-minute allotment.
Yep, you're just right at 10 minutes. Thank you guys so much for your presentation. I'm so impressed with the video quality from the cruise. I can't believe that you were able to make that happen. All right, so
Thank you.
yeah, right. I know. So heading into our Q&A, was there anything from our judges that we'd like to initially address before we get to the list of questions? Fernando, looks like you raised your hand. Go ahead and unmute.
Yeah, so understandable that you're working with a utility that has generation. How would this apply for utilities that don't have wire-only utilities that own just substation with SCADA? Would it still be in process or will it be different?
Great question, Fernando. Hingham actually owns generation, but they're also the distribution utility as well. So they're a full service utility. So let's pretend for a minute that Hingham didn't have generation. They're just an investor-owned utility that can't own that stuff. The SCADA environment's still the same. So all that data from all those smart grid field devices, they're all talking DNP3 up to the SCADA station. Once it gets to SCADA, that's where this entire concept could apply. So Same use case, station loses power on the supply side. Smart contract exists, looking for zero voltage detected. Notifications go out to all critical notification receivers, police, fire, emergency response, things like that. But at the same time, it's getting published to the chain.
All right,
Great
thank you.
question.
Looks like we had one more hand raised.
Yes, so very interesting concept. Like two questions. One, in the prototype, it's not clear that how the blockchain capability, like let's say Ledger, is being used for the security. And maybe I can ask second question later, but once it's in place, what will happen to the centralized SCADA?
Hey,
Yeah,
that's great. Luke, I'm gonna let you take that one.
yeah, take a stab at it. So security in the ledger, Hyperledger Fabric is a private permissioned blockchain for multiple types of organizations to share ledgers across channels. You can imagine government or fire department being an organization in that and having a replicated ledger that they have secure access to, without having to have multiple other integration points to share some of that siloed data. So inherently, there's built-in a public key infrastructure, PKI, built into the Hyperledger Fabric offering, open source offering. It's partnered with IBM and the Linux Foundation. And through that, you get security in your ledgers and are able to decide which information is shared. So the smart contracts provide access to the ledgers that's underlying, and each organization owning the data that's being reported. So voltage being reported from HMLP would be their organizational data, and they can decide which participants can join and which pieces of that data they actually have access to, while the whole ledger is immutable and trusted and can be looked back at for verifiable metrics and data.
And Luke, just one more thing to add with the SCADA. I should make sure it's very clear. No one on this call is trying to kill SCADA. I don't want that on my resume. What we're saying is that SCADA can coexist. This is a process to make SCADA interoperable with everybody else. So SCADA lives on.
Yeah, so the second question was that, is it going to coexist with the centralized? And if yes, then is the plan is that, say, microgrid or a smaller scale will be with chain SCADA and the distribution and transmission will be with the SCADA?
Excellent question. That's something that's going to have to get figured out with the utilities and the DER operators. Ultimately, the both can happen in tandem, right? Because the access to the data at the edge, right, could happen on that ledger that Luke's talking about. So the DER operator that's looking for a zero voltage instance, they could be subscribed to that open database from others that are having impacts. So they're not directly plugged into SCADA, right, which is a major safety concern that we all have. So the edge operator that has the solar panel, they can be saying, hey, is there voltage issues happening other places in the grid? On the flip side, they can be sending their information up to the utility or the ISO or the RTO SCADA system via SCADA DMP3. So they live together, if that makes sense.
Sounds good. I do have more questions, but I'll ask later.
Thank you. All right, looks like we have two more hands raised. Whoever would like to go first.
Sure.
Hi, Robert.
Can you hear me?
Yes.
Okay, so my question on this, it seems to be that the solution here is taking the operational data from generation, transmission, and general grid information from the SCADA side and putting almost sort of a business and notification logic around it to allow for interoperation and general information awareness, grid planning, and things of that nature. How does this differ in functionality from conventional ICCP and secure ICCP systems that are typically used between differing SCADA systems to share this information?
Robert, that's a great question. Yeah, so one of the challenges is we talk to the other industry operators, police and fire, like this thing called CAP protocol. It starts to get more and more confusing when they're like, hey, I just need key bits of information that zero voltage instance would mean my streetlights are out. So creating a mechanism that makes it more usable. And then also when you look at like a traditional, like you said, like the SCADA environments, if I do want to follow today's workflow, and I'm the police officer right now, I want to know that power's out at the streetlights in my town. I'm waiting for it to go from SCADA to a historian to an outage system to some sort of data logger or database that has an API on it that I can subscribe to. And then it's always this one-to-one. This environment we're talking about creates a one-to-many, right? So the utility, once it gets to the chain and they have their pre-authorized users that can access that information Luke was talking about, at that point, it's real time. So the second you see that anomaly, the smart contract, that's when the third parties could start to see this information. So the goal here is make it easier to play across the different industries, but then also for like utility, if you want to cover that aspect, I think that'd be a great point.
Yeah, and also too, it gives access to the singularity level of a utility, not just the system in a whole, but down to a feeder or to a reclosure or to a Lindsay sensor. Data that can actually be used to perform interconnection studies that could just, a consultant firm or a project firm come in and just grab all the data. I mean, we get asked on a yearly basis numerous times about distributed generation assets, feeder assets, feeder numbers. So being able to have this open is actually something that would benefit a lot of utilities.
Thank you.
Oh, hi. I have a couple of questions. This is really good concept. One question I have is, so in your example, you have this voltage event, and you detected that. Are you able to tell the difference whether this is a voltage event caused by fault or it's actually a voltage event because of some kind of cyber attack? I guess that's the purpose of this hyperledger. You want to detect a cyber attack, right?
Mang, that's a great question. So what we did a giant SCADA mapping exercise to look at all the data elements and the devices. And I think it's in the report we put together, but it's a lot, right? But the key piece here is any pre-existing device, sensor, asset in the substation that's reporting data up to SCADA can be used to have smart contracts written against it. So for like a fault detection, that opens up the ability to have multiple different fault indicators across the entire substation down to end of line, like a fault sensor that's out there, all of them participating in it. We did go as far, I didn't even say this in the next steps, but where the code lived today was on the DMP3 master for the SCADA system, right? But one thing you could do, which would be super easy, is if you had a third-party device manufacturer that had sensing capability at the edge, maybe at the water utility, right? Something like that. They could actually install this code and capabilities and have smart contracts running at the edge. That's totally in the realm of possible. So you could even get closer to the actual edge devices pumping this information up. Yeah, awesome question.
Thank you for the clarification. That's clear. So another question is, I guess I didn't see it in the proposal. You have the metrics about how much you can improve the performance in terms of using your hyperledger solution versus the existing ones utility are using. I guess this is just a clarification.
I'll give you one. Typically, the outbound notifications, right, just on awareness that you've got an event, typically takes a cycle of about 5 minutes. And then this would be sub-cycle if you have the confidence in the smart contract to publish. So by eliminating all those other integration points at the utility, you could have the true concept of device level messaging happening off of, because you're going right to the system of truth and then creating a system of interoperability. So that's an easy metric. And Stephen, can you nod your head on that one?
Yeah, 100%. Listen, we have an anomaly on our system right now via SCADA. Whether I see a fuse cut or blow, it's within cycles that we get notification on our current SCADA system. So yes, like Zach said, if we take away some of the middle pieces, you can get instant notification.
Appreciate that. Thank you.
Well, great. I think we're out of time for this team. I appreciate all the questions from the panelists. And then, of course, our presenters' time as well today. I do believe we might have had some questions left over and one from the Q&A, so we'll make sure to communicate those to the teams and make sure that anything that we feel like went unanswered that needs to will be communicated. So thank you guys so much.
Thank you. Yeah, appreciate it.
Thank you, everybody.
Thank you.
All right, perfect. It looks like we'll have Ben that will join us soon as a panelist. He's getting added right now. Ben, let us know when you can hear us.
I can hear you. Can you guys hear me?
Yes, and we can see you.
Fantastic. Awesome. Should I go ahead and share a screen?
Yep, go ahead.
Perfect. Let me do that. Everything I'm going to present is going to just be from a PowerPoint today. So I think if I put it in presenter mode, share that with you all. Do you guys see that?
Yes.
Perfect. We would have thought 4 or 5 years of Zoom and I'd be more confident in what I'm actually sharing to you all, but here we are.
All right, perfect, Ben. So as soon as you get started, we'll start this timer and you'll have that 10 minutes.
Okay, that sounds great. Well, thank you all very much for being here. As Carly said, my name is Ben Rashnock. I am an assistant professor at North Carolina State University, and we have been working with a power co-op in North Carolina to essentially try to predict the power outages that they're experiencing. This is work with 2 other assistant professors in the Industrial Engineering Department at NC State, Dr. Jordan Kern and Dr. Sarah Shoshani. Dr. Kern's expertise is in grid modeling. He has a lot of open source models of the electricity transmission grid in North Carolina. And Dr. Shoshani's background and expertise is very focused on uncertainty quantification and how to deal with uncertainty in simulations and in models. Unfortunately, both of them are proctoring final exams right now, so it's just me on the call. But we worked today, or in this project, with North Carolina EMC. So EMC is the oversight board of all of the 26 co-ops across the state of North Carolina. North Carolina is predominantly sued by Direct Energy. The co-ops provide electricity to low-income or rural areas. And one of the jobs of EMC is to help predict or help provide resources to these co-ops to make sure that they're meeting their operational challenges. So we partnered with them, and they expressed that one of their big problems was being able to anticipate disruptions at a very particular scale. So we spoke with them, we asked what their challenges were. They came to us and said that if there's a Category 5 hurricane approaching the coast of North Carolina, they know what to do, right? They're able to prepare for that. They're able to dispatch resources down to the co-ops. They're able to activate some funding and some staffing decisions that they have so they can provide additional staffing resources for the 36 co-ops. If there's a really bad hurricane coming to the state of North Carolina, they know that they need to do that in advance. Similarly, if it's a bright sunny day, right, there's no forecasted severe weather for the next few weeks, they know that that's a situation that they're not particularly concerned about. But they have been caught off guard a few times in the last couple years where there has been a severe thunderstorm that they didn't anticipate leading to outages, then it did lead to outages, and they think they could have been better prepared if they were able to have some anticipatory knowledge of these events, and specifically making sure that these events led to some sort of power outages. So what we did is partnered with them to see if we could help anticipate these disruptions on their end and try to integrate it as best as we could into their logistical staffing decisions, their prepositioning of supplies, and their logistics decisions. So this is a problem that is not unique to North Carolina. This is not a problem that is unique to this EMC, to the co-ops in North Carolina. It's one of the larger problems that is facing at least the East Coast when it comes to severe weather outages or disruptions. What we ended up doing, or sort of at least to describe the overview of what we proposed, we built a big statistical model that takes in weather data, that takes in data from the built environment, that takes in data from the local tree density and environmental factors. We train a big statistical model, and we use that to try to predict where there are going to be power outages in the state of North Carolina with a little bit of forecast lead to it. So I'll note that we have used data from, they provided data to us to try to replicate the outages that they've seen in their co-ops. But everything that we're showing today is all using publicly available power outage data, so that this is easy to show. So we can talk numbers, or we can show these, and we're not providing any proprietary information. But we take data about weather, the built environment, tree density, we build the statistical model, and our goal is to try to forecast where there are going to be outages in the state. So if you're a numbers person, you're a statistical person, the out-of-sample predictive accuracy of these, the out-of-sample R-squared of these models is about 0.7. So we feel pretty good about this. There's a lot of work still left to be done in making sure that we're able to train this and make it a little bit better, but we tested a variety of different models that are out there. I'm happy to go into those details if anyone is interested, but this is a pretty standard cross-validated model selection procedure to make sure that we're not overfitting to this data, but we're still able to extract all of the trends in the input data that we're using. And to sort of look at some of the case studies that has been of interest to the EMC, we took a few different hurricanes and thunderstorm events and sort of went to validate these and verify these by running our model on these historical events, taking these out of our training data to make sure that we weren't, this wasn't something that we had, our model already had knowledge of. The first one we looked at was Hurricane Michael in October of 2018. And the number that was of interest to EMC, and the number that was sort of easy to talk about when we're reporting this, is how many counties were we able to estimate had a severe number of outages, which for them, we sort of landed around an idea that there'd be 10,000 people without power. This gets a little bit tricky because there's lots of counties in Eastern North Carolina that are very sparse. Some counties in North Carolina only have 3,500 or 4,000 people in them. So we're still working to figure out exactly what the right metric of success for this is. But the number that we, for sort of discussing model results, the things that we've been able to work on pretty easily, we say, how many of these counties that actually had a lot of power outages were we able to pick up? And for Hurricane Michael in 2018, which for all intents and purposes was a rather standard, meteorologically was a rather standard storm for the southeastern United States, we were able to identify 90% of the counties with severe outages. So that was a sort of a good starting point. These two maps that I have here, on the left is what actually happened, and on the right is what we predicted. The scale of these we have left off because we didn't want to. It was recommended to us by our utility to leave this off, even though it's publicly available data, just to add another layer of security to this. But for the most part, we do a pretty good job of estimating where they are for Hurricane Michael. That is certainly not the case for all of the storms that we tried. So Tropical Storm Elsa hit North Carolina in 2021. It followed this same southwest and northeast path through the state. And we did identify 100% of the counties where there were going to be severe power outages. And then we also identified about 20 more counties that we thought there were going to be outages in that didn't end up being impacted. So we did this and started to take this information back to EMC to say, maybe we should be thinking about alternative ways of identifying where there are going to be outages. Maybe just the number of counties that we are able to predict as severe was not the way to go. Obviously, there's a lot of statistical backing for different metrics that we can use, but we want to make sure that this is integrated into their decision making. So in this particular case, we very significantly over-predicted the number of outages that were there. And the last one I'll put some numbers up here for was a random sort of thunderstorm event in late April in 2021. This was not a result of any tropical system. This was just a series of bad thunderstorms. And using forecast data, using national digital forecast data to estimate all of the different wind speed and temperature parameters that are out there, we were able to plug this in as if it were a hurricane. Our model runs on the thunderstorms just as it does for hurricanes. And we were able to identify 88% of the counties that were going to experience severe impacts as a result of this thunderstorm as well. And this was really exciting because this is much closer to one of these difficult corner cases that the EMC was having a hard time figuring out if they should be staffing for or not, right? This is much closer to something that is a little bit questionable as to whether or not they should commit all of their resources to staffing these storms. Where we are on this project, sort of from start to finish, we started building this model. We got a bit of a late start. And so right now we have the statistical model that works pretty well. We're able to sort of make these forecasts or make these predictions. And where we are able to work on this project till the end of May. We've got the runway to continue on this through the rest of the spring. And so we've taken these results to NCEMC. They're very excited about the ability that we have to estimate these outages. But when we start talking about our overprediction or underprediction, our goal is to make sure that this is integrated with their actual supply chain, operational, and staffing criteria. How expensive is it for them to dispatch or to sort of fire up their emergency response crews if we didn't actually need to do that? what is that cost compared to the cost of not responding to power outages or not firing up their response center if in the situation where we needed to do that? So we're looking at balancing these costs, and something that we're currently thinking about trying to do is how do we adjust our predictions based on how these costs are? If it's very expensive to them to not respond to a potential outage event, we can tailor our predictions, or we can make sure that we are at least cognizant of our ability to over or under predict these. So the first thing we're trying to do is make sure that we're better integrating this with the decision making that's going on at the EMC. The other thing is making sure seeing what type of forecast data we can put into this model. This is really only useful if we have a 3 or a 5 day lead time. And all of these results that I've shown they're not using forecast data. They are using actual data, sort of imagining that we're predicting something for tomorrow. But unfortunately, when we have weather or meteorological forecasts, they have an implicit error in them as well. So there's a problem that we have to deal with, that we're also going to have this error that's induced because we're using a forecast, which is also going to be wrong. So we're thinking about, or currently exploring, different ways where we can approach this from a statistical context, and we also want to know how practical it'll be. If the wind speed forecasts and precipitation forecasts are always going to be pretty bad, well, then suddenly this is going to be a challenge for us. So we're trying to figure out how to add forecast data to this well. And then our final step will be to put this in some sort of a decision support tool, some sort of a visualization for EMC to use. The last slide I'll put up here was another challenge that we sort of experienced, and it sets up maybe some future questions or some interesting work that we've come across. Through the process of doing this, Hurricane Helene hit Western North Carolina, and a few of the co-ops that are managed by NCEMC were severely impacted by the damage from Hurricane Helene. So out of curiosity, right, we ran our model for the data that we had during Hurricane Helene, and then we compared it to the actual data that we saw. And so what's on the top is the estimated number of people without power, and on the bottom is the actual number of people without power. And so the long and the short of it is our model did a very bad job in Hurricane Helene. So this also opens up a lot of interesting questions. And how do we integrate this with EMC's decision making? This was a rather unprecedented event with unprecedented antecedent conditions. Is this something that we think is going to happen in the future? And how do we integrate this into some sort of a predictive model, given that there were a lot of other mechanisms leading to power outages compared to a sort of typical hurricane or tropical storm? So with that, I will open it up for any questions. I appreciate you all being in it for the long haul for a long Zoom meeting today.
Great. Thank you so much, Ben. Are there any questions that we want to address from the judges first before we get to our set list? Looks like we had a couple hands go up right at the same time. Whoever would like to begin.
Maybe I go first.
Perfect.
Very interesting presentation, a very interesting topic. I have 2 questions. One is, are you currently considering the grid topology in your predictions? So that's the first question. And the second question, because your predictions are going to be used for resource allocation, does it matter what is the cause of power outage? I mean, the same power outage can be caused by, like a big power outage can be caused by failure of multiple minor lines or one big major line. And then they require different type of resources. How do you account for that?
Yeah, that's a really good question. So it is something that we think may be a little bit out of scope for our first year of working on this, but it's something that we're eyeing to work with EMC on in the future. They have very good data about substation level outages. So they have we are looking at customer level power outage data, and they have a very robust record of substation level outages as well. So to your first question, we are not considering the grid topology. This is all the input data for this is all environmental conditions. But we hypothesize that there would be some clever ways to incorporate substation level outage data in this as well. What we've been kicking around as an idea is essentially a 2-stage prediction model, where first we try to estimate if there's going to be a substation level outage. And if we do estimate that as true, then that goes as an input into our customer level outage model. And the goal would be to be able to identify when there's a substation level outage. Obviously, this is going to lead to large amounts of customer outages. So one, we're able to better improve our customer level outage model. But two, when we start to dig into the predictive models, it'll help us identify what's leading to those substation level outages. Dr. Kern has done some work in North Carolina where he's found, and this is generally a trend for lots of coastal areas, that the substation level outages are caused by flooding for the most part in eastern North Carolina, and then the transmission level outage, the distribution level outages are caused by wind knocking trees down. And so our idea would be when we have these hurricanes, they have a compound wind and flooding aspect to them. We'd hope to be able to integrate the both of those. And we think it may be something that's useful for something like Hurricane Helene in the future, but at present, it's not something that we've included.
Thank you.
Okay, maybe I will go next. First, a very interesting presentation, and of course, this is very important work. Two questions. One is, kind of like a follow-up on the last one, that what features are being used, if not the power grid infrastructure model?
Yeah, so presently we are using environmental data. So this for us right now is tree canopy cover and built environment data. So we use the National Land Cover Database to identify the fraction of a particular county that is covered by different densities of trees and that is built, has different levels of development so that these are buildings and not rural areas. And then we are using weather data. So it's wind speed, precipitation, wind gust. So it's very external to the grid, right? This is all environmental or weather characteristics.
Okay. And the second question is that there are several other tools which can also predict the outages, starting from IBM to a lot of different startups in different part of the country. How does it compare with, because the features you use will just increase the accuracy, right? So as you already have saying on this slide, as we add the power grid network topology, as we add the infrastructure model, like how old the tower is, how old this, all those kind of things will increase the accuracy. And there are different technologies that exist and used by or proposed by different tools in the country.
It's a really good question. Through our discussions, this has been a very interesting work to do with the folks at EMC. I have an industrial and operations engineering background, and we talk a lot about decision makers or decision support. And it's very fun because we talk to the decision maker's name is Chris in this case, and we have one person who we're able to talk to. He is making the decision as to whether or not to activate resources or not. And so one of the things that Chris has discussed as being useful to him would actually be sort of backing out of the intensity of the statistical model and saying, rather than giving him a really high level prediction, which is something that is really detailed and has all of this data that's going into it, if there were some general rules of thumb to say when the wind speed starts to get above this, when the wind and the precipitation together both sort of increase into this area, that would be very useful as well for decision making. So this is something that we're letting the co-op help drive what's useful to them. But something that they've expressed interest in is even something simpler than a big statistical model. We could certainly use a model like this to identify those rules of thumb, but that may be something that ends up being more useful to them in their actual practical decision making.
Thank you.
Okay, maybe I'll go next. Hi, Ben. Yeah, I have two questions. So number one is I'm really glad you showed about the Hurricane Helene, which caused the flood in like 1 in 1,000 year event. You mentioned your model may predict poorly, but then there's also you may not even remember there's also a Hurricane Milton that direct hit Florida. People was really scared, but then it turned out the damages were not that bad. So it seems to be this really hard for the prediction. So I'm just wondering, have you thought about like for your methods? So AI methods are good at mimicking what happened, like historic data. But then either Helene or Milton, those may not be in the historical data. So have you thought about what ways you can or methods you have that can improve the accuracy of your prediction? So that's my first question. I have another question later.
So to answer the first question, we have been thinking about, I mean, this is a very large question for EMC that has really been put into the spotlight because of Hurricane Helene. And I sort of have the comments of it on this slide. We have largely asked them to say, how much of a concern do you think this is? We can provide evidence from the North Carolina climate reports to say we think that something like this, where there's heavy flooding in Western North Carolina, is more likely to increase in the future. But we are letting you all, help us figure out if this is something that we should be focused on. So when it comes to these types of unprecedented events, something like a Milton, something like a Helene, where there were sort of different intricacies to it, we're letting them call the shots. Something that I don't know if it made it in the slides, but we're very interested in making sure that all of these estimates have credible intervals around them, or some notional idea of a confidence interval, so that they also have an understanding of how good we think our predictions are for a given area. That was something that was very exciting to this decision makers, to the stakeholders throughout, was making sure that we were able to also estimate the uncertainty around the predictions that we're making.
Okay, good. So my second question is, so for your validation, for example, the Hurricane Michael, you said you predicted 90% of the counties that had outage. So my question is the spatial resolution at the county level enough for the utilities to make informed decisions?
That is a great question, and it turns out that is the heart of a lot of this prediction, is figuring out the right spatial resolution. So for our purposes, a county level was appropriate because the EMCs in North Carolina, just because of the way they have been developed, are generally on the scale of about 1 or 2 counties. So they are not perfect subsets of every county. So we actually have data at, you could imagine, the EMC county pair. So there is a county and it could be served by multiple co-ops. So we have the data at the county co-op pair, but for the most part, we are able to aggregate this to a county level. And we've tried different levels of aggregation, and they've all worked about the same. It is possible, certainly, to make a more high resolution prediction with more finely resolute data. And we're trying to figure out if that's something that would be useful or not. For now, counties have been convenient, but it is certainly something that is of interest to us to explore in the future, as to whether or not we could make this a higher resolution. One of the big problems with counties, especially in North Carolina, is that there's a very strong disparity in the density of counties. So Wake and Mecklenburg counties contain Raleigh and Charlotte. They have multiple millions of people in them. And again, as I mentioned, there's other counties that have 3,000 people in them. So it does present a data challenge in making sure that we have sort of nice looking distributions of the number of people, or if I'm predicting the fraction of people without power, or I'm predicting the total number of people without power. Those are very different if I have counties that have 3 orders of magnitude different population. So it has been a challenge, or something that we've been thinking about from start to finish.
Thank you.
All right, I think we're going to run a little short on time for our next questions, but we'll make sure that anything that wasn't answered today is communicated to you, Ben. We really appreciate your time.
Yep, thank you all.
Great, so it looks like we will be welcoming a few more people in for our next presentation. Give me just 1 second to get them as a panelist, and then we'll begin. Hi there, can you hear us all right?
Yes, I can hear you clear. Good morning. Can you hear me clear?
Yes, you're all good to go.
Okay, awesome. I also have a PowerPoint file. Let me go ahead and share my screen.
That'd be great, thanks.
Okay, do you all see my screen?
Yes.
Okay, awesome. So I just go ahead and start.
Yep, go ahead and I'll start your time.
Okay. Good morning, everyone. This is simply, I'm currently an associate professor at the University of Houston. Our project title is EV Load Accelerated Cable Failure and Replacement. So we are the RPG lab team. I'm the team captain, and we also have 4 additional team members. They are my graduate students. So our utility partner is the Centerpoint Energy that serves the greater Houston region with over 2.8 million metered customers. So this is our utility team. So Dr. Eric is the VP of Center Point Energy. He is our main contact. We also have a partner who providing admin related support. And we also have a technical utility support team of 4 of their engineers. So we have weekly meetings when we implemented the solutions. So let me first explain the challenges we identified. So as you all know, power cables are part of the key power grid infrastructure for delivering electricity to consumers. Cables, they always carry some good amounts of electric currents. So when the electrical demand increases, then the cables need to carry higher amounts of electric currents. That will lead to an increase in cable operating temperature. As a result, the cable will degrade faster. And also in recent years, electric vehicles have been growing very fast. In other words, this will substantially increase the electrical demand that will reduce the cable lifespan. So we need timely cable replacement. If that is delayed, it may lead to longer outages to some communities. So to address this challenge, we propose a data-driven approach. We mainly worked on 2 tasks. The first task, we projected the future EV adoption rate and the future load. With that, we continue to the work and estimated the cable degradation and predicted the cable remaining useful lifetime. One highlight of our work is our analysis was done at individual substation level rather than at the entire system level. This slide lists all the data we used in the solution. So we studied a single large substation with over 3,000 residential customers. So we use the network data, multi-year time series meter data. We also have the level 2 EV charger registration data. We also have the detailed cable material information. We also had to use some publicly available data sets to implement our solution. So once we got the utility data, we first did some data pre-processing. We analyzed their data. So it's a lot of data. So we found that some data points are missing. Some of them are weird. So with the feedback and support from our utility team, we were able to impute some missing data points and did some correction as needed. So in our task 1, we first implemented a least square method using the historical data from both non-EV meters and EV meters. And our estimated average charging power of existing installed EV is 9.9 kilowatts, which is consistent with the commercially available level 2 chargers. So this is the average charging power. So once we got the projected number of EVs in the future years, then we just need to multiply by this average charging power. So that's how we got the EV load. So we implemented several regression methods to do the EV projection. In the second task, we first implemented a 7-layer underground cable thermal model. So as you can see, this is the cross section of an underground cable used by our utility. So we implement this cable thermal model. So this cable thermal model is used to map the cable power flow, or say cable currents, onto the cable operating temperature. Next, we implemented the Arrhenius aging model. So this Arrhenius aging model, it can map the cable operating temperature onto the expected cable lifespan. So if we operate the cable at a constant temperature, this is the expected cable lifespan curve. So when the cable operating temperature is high, then we have relatively low cable lifespan. Okay. So this slide shows the overall solution procedure. So first we analyze the utility data. We obtain the historical electric demand information, and then we did some regression projection to estimate the future electrical load, including the growing EV charging loads. With that information, we went ahead and calculated the time series cable currents, like how much electricity, how much electric currents those cables need to carry over time. In the third major step, we use our implemented cable thermal model and calculated the time varying cable operating temperature. Then this information was sent to the cable aging model. So with the aging model, we were able to estimate the cable remaining useful life. That's how we got the expected cable failure time. And with that information, we have a much better idea regarding when we want to proactively replace those cables in a timely manner. Okay, some key takeaways. For the last mile lateral cables, they directly connect serve the end consumers. So our utility partner, they were worried about faster degradation on their lateral cables, because lateral cables, they use smaller conductors with lower ampacity. However, based on our research, those lateral cables will not experience substantial degradation due to EV growth. Even under 100% penetration, EV penetration, they won't degrade more than 1%. The main reason is lateral cables, although they use small conductor, they only serve very limited of consumers, roughly 30 residential customers on average. Another type of cable is the main feeder cables. So they use larger conductors. They have higher ampacity, so they can carry higher currents. However, for the main feeders, they serve much more consumers, so they often need to carry a much larger electric currents. As a result, those main feeder cables, particularly those that are close to the substation, they may experience substantial lifetime reduction. We need to pay closer attentions. We had very active interactions with our utility partner. We had 5 meetings in the planning phase to identify the challenge and propose the solution. In the progress phase, we had weekly project meetings. It's online, but we also had one in-person meeting. So this is a group photo we took during that in-person meeting. For our next step, so we are conducting additional tests. We are trying to we're improving our methodology, and then we'll scale up the work from a single substation to our other CMP substations. Since many other utilities they have the similar issue, they also observed fast EV growth. So this work can be potentially applied to many other utilities. And we have been continuing our meetings with our utility partner even after we submitted the phase 2. For example, we will be meeting with the utility technical support team this Friday, and we'll be meeting with the VP next Monday to discuss and finalize our next steps. That's all I have. Thank you.
Great, thank you so much. You were right at time. Do we have any questions from our judges that we'd like to begin with? Sarah, I see your hand.
Hey, good morning. So I might have missed this, but is your objective to help your utilities understand when they need to replace their cables, or is this just information for them to make their own decisions on how to best proceed?
Good question. I would say both. So since we just started this project less than 4 months, right? So the phase 2 is 4 months. So the initial goal is provide information for our utilities so they can have a better idea when their cables will be will need to be replaced. I think as we continue, this probably will help them make the decision when they need to proactively replace their cables.
Understood. Thank you.
Thank you.
Thanks, Sarah. Looks like we had 2 more hands.
Yeah, hey, Xingping. So nice presentation, and I
Thank
think it's an important problem, but is it applicable to all different kind of cables or certain voltage and certain current? And what about surrounding and environment of that cable? Because some will be going under the building, some will be going, underground, and how does it impact your assessment?
That's one good question. So yes, so for first question regarding the cable type, so we implemented this underground cable storm model for our utility partners cable. So it has 7 layers, right? So this is an underground cable. That's why it has so many layers. It's buried underground. That's why it has 7 layers. The thermal we implemented covers all 7 layers, and also this thermal models can take the ambient soil temperature as input. In other words, we can capture the impact of the surrounding air or soil temperature. So we don't have the soil, the underground soil temperature, right? That's why we had to use collected our own public data. We collected the time series ambient air temperature. Then we map the ambient air temperature onto the underground soil temperature. So that mapped underground temperature was used as the input, part of the input to our thermal model. Short answer to your question would be yes. So our methodology can capture different types of cables and also capture the surrounding temperature impact. Thank you.
Hi, I had a question, but I just looking at this, I came up with another question. So have you modeled any overhead cables as well?
Good question. So for this particular project, we only focus on underground cables. Because for the substation data they provided, majority of them, they're underground cables, including all of the lateral cables, the last mile lateral cables. That's why we focus on underground cables. But our next step will be implementing a different thermal model, maybe a much simplified thermal model for the overhead lines. For the overhead lines, they don't have so many layers. So basically, it's an easier job, I would say. Thank you.
Okay. And I had a question about your future work. You said you would be doing some more testing. Could you speak a little bit more to that? It seems like you guys made a lot of great progress. So I'm wondering I'm a little bit more curious on what comes next. Thanks.
Yeah, thank you. So for the substation, the system we studied, there are like 100 lateral cables, right? The last mile lateral cables, there are 100 of them. So we only studied like 5. For instance, we picked the lateral cables with the highest number of customers. So we started that. We didn't study all of them. We just picked the lateral cables that may experience the greatest cable currents. So they may experience the worst cable degradation. That's why we picked that one. So we didn't start off there. Maybe we need to study all the lateral cables to make sure our conclusions are also correct for other lateral cables. So that's some of the additional tests we are doing now. Yeah,
Thank you.
Great. Did we have any other questions that we wanted to address before maybe we took one from Jim? Ming, go ahead.
Hi, Xinpeng. So, one quick
Hi,
question is, in terms of validation, did you try I'm not sure whether I saw this in the proposal. Did you try the validation of based on the historical load data, then you calculate the current increase and also you calculate the temperature variant versus the measured current and the measured temperature in the using the historical data?
Thank you for the question. It's validation is very important. So we initially thought we would do some validation using some real utility data like the cable lifespan for some cables they already replaced, right? But unfortunately, our utility partner they don't have such data. They did not record their the cable, the information of the cables they already replaced. But one thing we did verify is some of our models implemented. For example, they provided some cable manufacturer data. So they provided giving operating temperature and also they associated the cable lifespan, right? So we verified our model with their cable manufacturer data sheet. So that's something we some validation we have done. But unfortunately, we couldn't verify the entire methodology because of lack of real data.
Thank you. Thank you for the
Thank you.
clarification.
All right, we have just about 45 seconds left if anyone else has any questions. Otherwise, I think we can conclude this Q&A.
Okay, all right. Thank you so much, everyone.
Thank you so much for your time. We really appreciate it.
Thank you.
All right, so I will go ahead and promote our next panelist. Give me just one moment. Ross, you want to let us know when you can hear us?
Yeah, I can hear you. Can you guys hear me?
Yep.
Perfect. Just share
Will
my
you have Shane joining you today?
Yeah.
Okay. Keep an eye out for him.
Yeah. I think I'll be doing most of the presentation. I think Shane's mainly for Q&A. So if he comes in a little bit after, that's fine.
Yeah. Yeah, I'll keep an eye out.
I believe he might be listed as R. Powell if you can't find Shane.
I don't see him in the attendee list, but I will keep looking. And we can see your next slide. It's not just your primary slide.
Okay, sorry, I'm stop sharing the wrong one. There we go. He says he's there.
I'll figure that out while you're on your.
Perfect. All right, can you see people see the correct screen now?
Yeah, it's just your primary slide now.
Yeah.
Great.
Perfect.
All right, well, I will go ahead and start your 10 minutes when you begin.
All right. Thank you, everyone. My name is Ross Connor. I'm the Director of Geospatial Data Science here at earSource. Joining us will be Shane. He's the Manager of Power Delivery, Analytics, and Innovation. Quickly moving through, what we want to do is just talk about the challenges that we're trying to address, the concept to address them, demonstrating what we've done, and then talk about the impact. Challenges what we have is any analytics project that we're trying to do involves multiple different data sets across different data silos. The GIS data, asset data, outage data, and a variety of others. These data sets were designed to manage their own type of data. They weren't designed to work with each other. So compiling them into a useful analytics environment is time consuming and expensive. Additionally, the owners of those data sets, each of those data sets have their own owners. So the GIS team, the outage team, power delivery teams, they're updating and improving and adding new features to all these data sets independently. And that's also, so there's change over time happening all the time. So when we do a compilation for an analytics project, we have an understanding of the current state, and that current state is just for that given point of time when compilation is complete. We don't understand what the system was like moving backwards. And we also don't have if there's changes in the system, like 5 minutes after, 15 minutes after, 2 days after compilation, we lose those updates. So what we're trying to do really is just decrease the compilation time by having a standardized data platform that has context, both tabular from all the different data sets, the spatial context between all those data sets, and the graph functionality between all those data sets. Create a digital twin to improve our initial understanding and quality of the data, and that will reduce compilation time and let us deliver more analytics project faster and garbage in, garbage out for all these analytics projects. So better quality data leads to better analytics. I'm just going to quickly hop to presentation.
Alabama Power Company partnered with eSource to create an enterprise-wide spatial graph database. The system provides an analytics-ready dataset for AI and machine learning, increasing the speed to value of analytics projects. The Enterprise Graph DB is now deployed and is providing Alabama Power several key benefits. The system is a digital twin providing pre-validated conductor mapping with power flow, protective devices, transformers, and meters. The system also serves as a data stewarding support tool, monitoring data discrepancies across source data. The graph's slowly changing dimensions functionality maintains a full history of changes and historical grid configuration, allowing for more accurate reporting on the impact of reliability programs and operations. 2 reporting use cases have been deployed. The first is conductor ampacity analysis, which retrieves the minimum ampacity along various paths in the network, supporting stakeholders to adjust SCADA alerts appropriately to better support grid operations. The second is non-SCADA momentary outage identification. Leveraging the topological functions of a graph database and machine learning, this analysis allows APC to predict and monitor areas of the distribution network for recurring non-SCADA momentary interruption, which represent a risk for upcoming sustained outages. Historically, these momentaries have been a reliability blind spot. eSource is now exploring what's next with our project partner and is prepared to ingest new datasets or deploy additional use cases for Alabama Power.
So quickly just going over the design of what we're doing, we have these variety of different data sets here. We talked about the data silos. These are typically served out on Azure. We will migrate them into a Databricks environment, and these are all ingested, and they go through 2 different sets of QA. The first QA is just sort of looking for individual records, like QA at the individual data set records. So are there missing records? Are there weird values? Are there missing values, stuff like that. Any issues that we see is recorded in a data quality log, and then that can be served up in a dashboard to allow the data owners to understand, like, hey, something might be weird here, let's investigate further. The second layer of QA is validating the data sets against each other. So, hey, if we have an outage or if we have an outage and there's no device associated with that outage, that's a question mark. We have vegetation management work that is a mile away from any conductor that we have mapped. That's another question mark. Again, these issues are logged and then brought up to the data owner so they can look at and investigate those records moving forward. We also build our graph topology at this step. So we have a goal table that's basically fully enabled, has nodes and edges for the power flow and direction. So we have basically a map of power flow throughout the whole system with associated information from other data sets. We deposit that into a graph database, and then that graph database can be queried to create a customized analytics environment for a variety of analytics projects. So we're able to query out the important information for what we want to do and move forward with the analytics or start exploring and modeling that data right away. The pipelines we've built, really the first pipeline is just combining the data sets, checking, loading currently. Every time there's enough refresh, we'll load that data in, we'll run our QA checks, and we'll combine that data. The second thing is basically enabling that graph functionality, creating the nodes and edges, giving power flow direction, and also attaching the devices to the nodes. So we're able to segment up that power flow. Talking about the benefits we had, first project was just any input, any meter. We look at all the meters that are under that same system, and we look at the outages, the momentary outages. So momentary outages are outages that have been under 5 minutes. And we're able to compile that for 30 minutes across all roughly 2 million residential meters. And the other big improvement is because we're recording changes over time, we're able to say, hey, that outage occurred a couple months ago. What was the system like a couple months ago? So we can understand what that system was like at the time of that outage. So we're not saying this is weird or incorrect. It's like, oh, we understand how the system was designed or was set up at that time, so we can understand those outages. Quick demonstration, power flows going from north to south. These green devices are all not displaying any outage. These purple ones down here are displaying an outage. It's really easy for us, because the data is set up in this intuitive way, it's really for us to identify, hey, this is the operating device that operated during that momentary outage. The other thing that was mentioned during the video was the ampacity query. So we're looking at devices to help set SCADA alarms to assist automated restoration. We're looking for a given SCADA device. The graph query is really, it makes really easy to just write a query to just say, hey, what's the conductor associated with this SCADA device? And then what's the minimum ampacity for that conductor? And then you're able to report that for that device. What's the minimum ampacity for that? And then you're able to set a more intelligent alarm. This has a lot of benefits. For the previous way we did it, we were doing sort of spatial queries like, hey, which conductor, we were kind of crawling along the conductor spatially, but you would have intersection issues. If something was going across your system rather than along that line, you would collect that too, and you get sort of incorrect readings from that. Because we're actually mapping the power flow, we don't have any of those intersection issues we had with our previous methods. The last benefit, just really talking about the benefit of the reports of data issues that we saw. So I think it's a big benefit. We're enabling the data owners to improve their data and understand, communicate effectively with their own data without putting extra work on them. Like, we have a dashboard they can look at and address as they have time and ability to. So what we have is we have partitions, basically, which are just connected components, series of connected components. The first pass we did, we had 451, which is roughly the number of feeders in the system. But we also had these roughly 1,500 underground small things. So these are basically sort of islands of disconnected components from the rest of the graph, which is about 2% of the system, which is still pretty good. You have 98% things. But because we're able to tell the APC GIS team, hey, these are the disconnected components, they were able to address that and basically had rounds to zero number of issues of that. So the whole system improved its connectivity for that. And so really demonstration of, like, once we're able to demonstrate the issues, we can, once we're able to say, hey, these are things we'll be looking at, they can look at and improve it. And you get this positive feedback loop of data quality, improving data quality, because now that we have better improved geospatial connectivity, that might improve our outage mapping or our vegetation mapping, and then they might bring up additional things, and they can keep improving their system. There's this positive feedback loop of all these data owners being able to improve their data, which feeds back into the system. So we just have this validated, up-to-date, continuously improving data set for our analytics projects. I'll take a breath there.
Yeah, it looks like we're right at our 10 minutes. If you're ready to take some questions, we were able to get Shane on the line.
Hey, Shane.
Hey, glad to be here. Thanks.
Thanks for joining us. Were there any initial questions from our panelists? Oh, perfect. We already have one hand.
Yeah, very interesting. So how often this graph need to be updated, and what would be the process for that if the outage happens, or basically one line goes out of the system, or networking? And is that graph is only for the electrical network or also for the communication network?
So right now it's just for the electrical network, and we basically update the graph at a cadence that aligns with the other system updates. So I think the GIS, because this is all being pushed to cloud infrastructure, so that is at a weekly cadence. So basically, data's being moved to the cloud infrastructure on a weekly cadence, and then we'll automatically ingest and update and push that through and regenerate the graph basically as needed on that cadence. And if the cadence for cloud updates increases, we can increase that right now, but right now it's weekly. So
it will be the whole graph network, or you have the abilities to update the one edge of the graph?
yeah, so what we'll do is it's a really good question. So we don't rebuild the whole graph. We say, here's the graph, we know what changes are there, and we're able to say, basically make the existing, like if they replace a line, say, hey, this old line or device, move it to obsolete or not currently active, and then put a new device in there and then build the topology around that new device. So it just continues to update. So we're able to say, and because we have these timestamps, we're able to say, what was it a month ago? We're able to requery that and say, what was the graph like a month ago versus what's the graph like right now? So we're able to put in, you're able to traverse the graph temporally as well. So like, what was it at a given time as we're able to build that out? Shane, I don't know if you have anything you want to add there.
Yeah, that's actually a big utility problem of understanding how your investment over the last year changed your system. So like I'm in charge of reliability too. And so you make all these investments and you can see a delta in your reliability, but you don't know exactly how weather affected it versus your infrastructure. And to be able to kind of go back and traverse what the network looked like a year ago and then play it through current weather, you're really able to isolate something that we can't isolate today, which is how did your investment affect reliability and not just weather plus investment.
Yep, sounds good. Thank you.
Fernando?
Question, how would this apply for a utility that doesn't have a lot of the devices and other items, components, information that you may require? Like maybe they only have AMI, would it still apply? Would it still be able to work with that? Or you need to have like, SCADA or deployable sensors already in their circuits to be able to implement something like this?
I'll be happy to
Go ahead.
join in there, Ross. No, I think it plays better the less the less automated and scalerized your system is, the less you know about it, the more the graph actually helps. So we're a very automated system from electronic communicating devices, SCADA devices. What we're trying to find out is the ones that can't talk. So like a fuse or a smart fuse, a dropout recloser, a trip saver, or whatever. When those devices operate, but they're not connected back to the SCADA network, you really don't have insight into that. And so the graph database gives you that insight that you wouldn't have. So in my opinion, the less automated a utility is, the bigger edge gap this is. But kind of the big thing going forward is really, if you are extremely automated with like AMI and SCADA devices, the historic replay analysis will be huge for us understanding investment, but it really also puts you on a good path to do advanced distribution networking modeling, like kind of moving forward past where we are today in the industry with SIGN.
Oh, okay, nice. Thank you very much. Great answer.
It looks like we have another hand raised.
I have a question about the scalability of your method. Like in this table, we see the number of partitions are about 2000. Can you let us know how you imagine it would work if you have more number of partition for a bigger utility company?
Yeah, honestly, the infrastructure we're using is really scalable. So we're using Databricks for the data processing. That's a large big data component. It's used to handle big data sets. And Neo4j, which is the graph data set, is a graph database we're using to generate our queries. Credit card companies, finance companies, they're building a graph of their entire consumer network. All the customers, all the things, every credit card transaction, etc. They're able to handle that without any issue. And also the other thing is like the validation that's going into it. Like once we generate our analytics environment, we can just query that out once. So we're not continuously querying it, which is a nice benefit in terms of maintaining costs. Like we can if we want to, but a lot of the use cases are able to sort of like generate it and then update it as needed rather than continuously referencing it at all times sort of thing, like pinging it every second or something like that. So I think it's the the technology is very scalable, and I think we're barely scratching it. Sorry,
Yeah.
Shane, you can add on to that.
Well, for Alabama, we tried with a small use case at first, but we're roughly 88,000 miles of line. Southern Company's probably 160,000 miles of line. So, we definitely built this project knowing that we would have to take 2-3 states worth of distribution network. So I think it's very scalable from a nationwide perspective in the utility landscape.
I see. Thank you.
Yeah, thank you for the clarification. Were there any other questions we wanted to address before maybe taking one or two from Jim? Megan, go ahead.
Oh, hi. Just one question here. So, is Alabama using a single version of the data, or you have multiple versions? For example, for planning an operation, sometimes you might have to keep multiple versions for the data sets. Is this the single version or it's a multiple one?
We might have lost Ross.
Oh, sorry, I'm here.
You're there.
Yeah, so we are using the current GIS data, but like we said, we are recording changes in the system. So as all of these systems are updating, we're recording as soon as they become part of the system of record for each of these data sets, we're communicating them, and then we're also recording like when something is no longer part of that system of record, we still have it, and we just say, hey, this was current as of these 2 dates, and then with the current date, so you can kind of traverse both across time. I'll let Shane add on. I'm not sure if I addressed the question there.
I hope you did, but yeah, I think from a utility perspective, we kind of only keep a single version of the data, so we only have like what's live right this second. I've been asked multiple times, can you go back and see like how many reclosures or how many line miles or how many poles we've added over time, and you can generally get like a vague sense of, hey, we've added 1,000 poles in the last calendar year, but you really don't have optics into where or how many were removed and added. It's just a bulk change in your system. And we're believing that the graph database gives us those time-stamped systems of record of what the system looked like previously versus now. So it really allows us to do better analysis on the system.
Okay, thank you. I think it's really nice to have a unified database for the entire utility. Thank you.
Fernando, I think we have time for one more quick question.
Yeah, just real quick. So Shane, you mentioned that you can kind of use this to look at the investments that you have deployed. Have you done that already? That would be pretty interesting if you have, and can you speak on that?
So we have, so I'm going to go focus in on like a trip saver, a fuse saver, a smart fuse. Those devices, open and close without dropping the barrel, and it avoids a permanent sustained outage. You just get a momentary. Those are impossible to actually see the impact on your system. So we started trying to figure out, like, can we quantify, they're pretty low cost capital investment. Can we
Okay, that's great. And I know that's really useful for utilities for their PUCs to make a case of why they're investing and continue investment. All right, thank you.
Great. Thank you guys so much. We're right at time. We appreciate you, Ross and Shane.
Thank you. Pleasure being here.
Thanks, everyone.
All right, it looks like we should have our next team already as panelists. So whenever you guys are ready, feel free to turn on your camera, share your screen.
Hi, can you see my screen?
Yes.
Okay. So, hello everyone. My name is Bruno Paes Leão. I'm leading the Latios team here to present the Grid Care project developed in partnership with Holy Cross Energy from Colorado. We're now switching to track 2, right? So cybersecurity focus. And the motivation, the challenge is the identification of the most relevant potential cyber threats that can affect power grid operation. And we have, of course, methods out there that can perform analysis, right, to achieve this type of result, right, of information. But they, in general, are adapted from IT, right? So they consider the power system operation only indirectly, right, by means of abstractions. The goal here of the methodology employed in this project is to consider the power system operation directly into the cybersecurity analysis, right? Therefore bringing more confidence and relevant information that can be properly employed by the utilities to enhance the cybersecurity posture of the system. And how is this performed, right? So this diagram presents the 3 key blocks of the methodology, right? So starting at on the bottom left, we have a simulation model of the system that is used to quantify the quality of system operation by means of KPIs. On the bottom right, we have the cybersecurity information.
Sorry, is there any presentation being shared?
Yes, I'm seeing the slides.
Yeah, you might need to leave the call and rejoin.
Are you seeing the presentation then?
Yes, we can see that. Bruno. Yes.
Okay, so can I go on then?
Yes, go ahead.
Okay, so yeah, so back here at I think I was on the bottom right here, we have the cybersecurity information, right, which includes network communication, or sorry, computer network topology, or and also the device information in terms of the actions, so potential actions an adversary can take. And on top, we have this sequential decision-making optimization engine that interacts with the simulation and the cybersecurity information to search and identify the most critical cyber attack scenarios in terms of sequence of actions performed by the adversary that can create the most impact to operation as quantified by the power system operational KPI. And we have worked together with Holy Cross Energy to create representative models of the system. So this includes, again, the power system side, and for that we have included the whole distribution system operated by Holy Cross, and on the power system side, right, to gather all the information and compile so that we could successfully implement the methodology. From the power system side, as I mentioned, we have employed the whole system, the whole distribution system, and analyze the complete system. And we have used OpenDSS as a tool for modeling together with this tool called PyCigar, which is result from previous development in partnership with Lawrence Berkeley National Lab. And we have included on the simulation OT field devices that could be employed by the adversary to disrupt the system operation, which are interfeeder switches, feeder breakers, utility scale DERs, and AMI collectors. All those definitions performed together with Holy Cross, right, as well as the KPI, right, that was considered. We see in the bottom the equation here, but basically it is a combination of the loss of load and loss of generation. We see here there's L, so you may see my mouse pointer here. We have LT representing the loss of load and GT representing the loss of generation. On the computer network side, we have used this NetJSON format to compile and use all the information, but you have to gather information from different sources, which include computer network topology, information from each specific device in the system, that include also possible adversary actions that can be performed associated to each device and to each network link. So we also consider the links as they are so network-based attacks are also analyzed or considered. And there's also these action costs, right, that are used here. And it's a more abstract term, so I'll talk a little bit about what this cost means. And as well as this has also been an innovation, right, that was developed during the project, right? So I'd like to talk a little bit about that. This is a diagram depicting how the cost is calculated. I'll of course not get into details of this diagram, but I'd like to describe that based on three main blocks, right? So first, what we are doing is mapping actions to techniques, right, based on MITRE attack techniques, and devices to CVEs, so to vulnerabilities. Then we match vulnerabilities to techniques, right, and then back to the actions corresponding to those techniques. And finally, we use existing well-accepted information in terms of quantification of exploitability and controls to define numbers for these costs, then matching the identified vulnerabilities, right? So the lower the exploitability and higher the controls, the higher the costs, right? So those are what the cost means. And I'd like to present a little bit so what's under the hood, right? So make things more concrete. So let me show you quickly. So this is the visualization, right, of the computer network that actually represents what is there in Holy Cross, all anonymized, of course. Right, but we have all the relevant devices here, including communication network, control center, OT field devices. Right, what is under the hood here is this representation, this NetJSON format, right, of all each node being one device with corresponding information on possible actions an adversary can take and related costs, and also representing all the links, right, and with associated costs as well. And the analysis being searching through these three, right? So here I bring an anonymized small part of the tree, right, that is considered, but we have cyber states, right, representing how the information that the adversary has in each step of the analysis, right? And we have for at each state there's a number of actions that the adversary can take, and then a certain action leads to a different state in the system, right? And so on and so forth, right? And that's in the search through these trees, what is automated by the sequential decision-making optimization, right? And identification of the most critical path as quantified by the power system operational KPI. So back into our presentation. So we have successfully implemented and executed, right, the methodology and the analysis. We have identified not only one most critical scenario, but we have used ablation to remove parts of the models and identified alternatives, right, that an adversary could have, right, to impact the system. And the results, we achieved very interesting results. So with the 19 most critical scenarios identified, and interestingly enough, all of them related to 4 assets of the same type. Again, so naturally cannot get into more details, right, than what I'm presenting here, but those scenarios relate to relevant potential impact to the system operation. And results were discussed in detail with Holy Cross Energy, right? And these are some excerpts from feedback from Holy Cross Energy. So feedback was very positive. They mentioned the information can be very useful to improve the power system cybersecurity posture. The solution provides a consistent framework for removing qualitative personal judgment, right, which is usually there in traditional analysis. The proposed solution provides a mechanism to help guide cybersecurity decisions, which is, of course, the ultimate goal here. Right, and the automated analysis, as can be enabled by the methodology, is a great benefit for the industry. To the words of Holy Cross Energy, so we definitely see a potential for applying that in a larger scope, not only in Holy Cross Energy, but other utilities with a relevant potential positive impact. And that's what I had. So thank you.
Great, thank you, Bruno. Do we have any initial questions from our panelists? Jody?
Yeah, hey guys. And I'm assuming that they'll get, because I had a couple questions in writing, so I'm assuming that we'll get that feedback back too. But just out of curiosity, I mean, what is this ultimate product that will be delivered for the sector use? Is this a software product? Is this an open source that like utilities can go use? And is it going to be user friendly for them to be able to understand what they need to feed into it to get out something that's useful? Thanks.
Okay, thank you. So this is a software, it's not an open source software, right? But this is, as we have software implemented, and this it is, I say, in early stage, so there are definitely improvements that can be performed in terms of usability and integration with the solutions, but we have already all the means for integrating all the necessary solutions for use for not only by Holy Cross, but for utilities in general. And the methodology as described can fit, let's say, the use of utilities in general. Hope that answers the question.
Yeah, thank you.
Thanks, Jody. Sarah, I see your hand is raised.
Hey, do you have eventual plans to kind of create some of the more typical scenarios so that this is potentially more quickly implemented at scale? So, you know, like if you have a device that is a smart meter and XYZ, then this is a scenario that you might see and it might cost this much.
So the scenarios consider not only, let's say, the vulnerabilities for a specific device, but the analysis is on the system level, right? So let's say that there's, so it's very specific to the utility. So let's say that you have certain smart meter devices, right? But they are, in the case we had the smart meters being providing information to an AMI collector, right? So depending on how those collectors are defined, right, and what meters provide information for a specific utility, the impact can be different, right? So the goal here is not to identify, let's say, scenarios corresponding to a specific to vulnerabilities or to a specific type of device, but rather the system level view, which will certainly vary depending on the specific scenario for each utility.
So how do you see this, I guess, going large scale? It's right, like it's a lot of manual effort. Do you have plans for that for future state?
Yes, so and that's a good question. So here we already consider the whole system, right? The whole distribution system, right? Which is very nice. Of course, it's not a large system, right? But yeah, we have plans, and we have described this in our narrative, right? Of integrating information that is already employed, right, for other types of cybersecurity analysis that are already out there, and leveraging those for so that we can reuse them here or integrate them here, right? So that to make this easier for the utility to use that more generally. Yeah, but
Okay.
those are definitely considered.
Thank you.
Thanks for the question, Sarah. Were there any else from the panelists before we jump to Jim's questions?
So I'll just say the questions that were sent in were from Jody. So Jody, why don't you go ahead and ask whatever. Did you have other questions, Jody, that you wanted to ask?
I mean, I already asked one of them, but you know, again, and I think Sarah sort of touched on it, is like this at the end of the day, like this is going to have to be some sort of automated tool that can be updated, right? Because the attack scenarios this is not static, right? Like every day we're learning new scenarios, new adversaries, and it's going to have to be user friendly for utility. It's going to have to be quick and easy for them to put their information in and then get some sort of easily understood output for their own risk assessment and risk management purposes. And maybe because this is just like the first stage, I'm not really seeing it. So any additional information, that you guys can provide to us on what this, end state really should look like if we give you funding, it would be greatly appreciated. Thanks.
Right. So I think one key aspect for making this better usable by the utilities in general is to connect, right? This we have provided a big step in this direction, that is integrating with information that is readily available and can be automated, considered, right, in the analysis. So all the let's say the information that we are using when we are moving more and more into this direction to use all the standard information that would be already there for, let's say, NERC or other types of standard analysis that the utility would already perform. Right? So and other, let's say, available information available out there, like MITRE ATT&CK or CVEs, right? Then CVSS, right? So the information that can be directly collected and employed in the analysis. But we are also working, and this is not used on this tool, but we are also working on a graphical means for the user to interact with the tool, so that this can be more easily, the user can more easily identify or understand what is there and add the required information, right? But that's for next steps, right, of the tool. And I hope that that provides more information.
Yeah, and it looks like we can take one more question, Sarah, if you want to go ahead. We have about a minute left.
Yeah, I think you know, in my years in cybersecurity, things like this is a consultation kind of a scenario where people come in and it's very interactive. And so I think just kind of bouncing off of Jody's question and statement, I do think that if you're able to provide a way for organizations to be able to identify their riskiest assets and the scenarios that exist for those assets, in a way that maybe there's some initial consultation, but they're able to do that in a more automated fashion and without relying on experts to be on site or to guide them through the entire process. um I think it's extremely valuable, but I do think that it it would better serve the companies that you're serving, to have some kind of automated process for that. Yeah. Thank you.
Okay, thank you. Yeah, there are some aspects, right, of the data collection and especially the modeling side, right, that still will require maybe some consultation and some manual data gathering in case this is not there. So some information that may not be integrated, right, in some database. But I think that once this baseline is established, it's perfectly achievable, right? We'll say easily achievable from what we have right now to have this easily updated and the further analysis being fully automated, right? And so that say so once we establish a baseline, the utility can benefit from the solution even when the say updates are performed or the system changes over time.
Great. Thank you so much, Bruno. Looks like we're right at time for you. We really appreciate your presentation and answering
very much.
questions for us today. Looks like our next team up, we should have Colin as a panelist. Colin, do you want to let us know you can hear us all right?
I hear you. Do you hear me?
Yep, coming through great.
Wonderful. I'll go ahead and share my screen if now's the time.
Yep, now is great. And then will Philip be joining you today, or is it just you?
Nope, he's on with the customer right now, so
Just wanted
small
to
business stuff.
Well, thanks so much for
All
being here, and I'll start your time.
All right. Well, thank you so much. I'm Colin Dunn, founder of Fend, and we're here to speak with you today about our progress on the Utility Cybersecurity Challenge. A bit more about the team for this challenge here. Fend's a cybersecurity company founded in 2017, based in Arlington, Virginia. And on the team here as well, the Matanuska Electric Association. It's still a bit early in Alaska right now, so Jeff Myers, who's been leading the team there, not able to join this morning, but he's been fantastic in helping us work through some of the different applications that we've been seeing together and thinking about some of the use cases that would be really replicable across the energy industry nationwide. Matanuska is an electric cooperative near Palmer, Alaska, where they serve some 55,000 members. And we got involved with Matanuska about a couple of years ago through our work and relationship with the National Rural Electric Cooperative Association. It's been great working with MEA on this project because so many folks look to them for leadership in terms of not only resilience, but also cybersecurity, because things that work in Alaska, which is an incredibly harsh environment for utilities to deal with, and really the cost of data acquisition can be incredibly high when you have to go out to sites, sometimes by plane and dog sled, I mean, literally, and it's constantly dark this time of year. So the stuff that works for Alaska co-ops tends to be followed elsewhere, but beyond the cooperative community, the larger electric industry in the US, there could be benefits from what we're doing here as well. So a bit about the technology, at the core of what we do is we make data go in only one direction. And we do that with compact hardware. And I've got an example here of one of our all-in-one data diodes built for OT, built for operational technology, that gets data and turns it into light, shines it in one direction, and reassembles it, at times encrypts it, at times changes the format, but it does that in a physically enforced one-way fashion so that you have full electrical and optical isolation from one side to the other. Now, this is a technique in the data diode category that's been around for 20 years plus in the intelligence community, in the nuclear industry, where if somebody were to hack into a system, lives are on the line. But when it comes down to it, all infrastructure is critical to someone and it's worth protecting. And what we do is we provide a physical barrier to cyber attack, especially for legacy utility systems where these systems are, they might be 30, 40, 50 years old, and they might be here for another 50 years. We meet that equipment where it is, speaking legacy protocols, and turning that data into formats and getting it into the hands of people so that they can take action without having to worry about the way that modern, even IT cybersecurity technologies might impact a legacy OT network. So it's that physics-based approach that makes a lot of our customers happy, and we've grown from our first SBIR award and from the Department of Energy back in 2018 into a company that serves customers around the world today. We've got nearly 100 customers across energy, water primarily, and some manufacturing. These are folks that say, hey, I'm not ready to embrace the world of AI in my infrastructure, but I do need my people to know what's going on. And we solve a problem that's really about getting data into the hands of people that need it, whether they're feeding models or analytics platforms. We're making sure they have access to those tools in a safe way. And in our work with MEA during this project, we've focused in on a few key use cases. One, without naming names of manufacturers and OEMs, the engine control system, for example, we're turning big turbines, we're generating electricity and passing the status and the telemetry of that equipment through our one-way hardware. Think of it as a check valve for data with no physical way back in, from this equipment into historians, such that the engineering teams can get that data in real time. If you need to have reports out to regulators, this information becomes available from systems that otherwise want to live isolated behind an air gap. But one of the really interesting ones that came up during our project is the ability to pull data out of security information and event management systems that are deployed on OT systems. Now, MEA is really forward thinking. They say, hey, I've got equipment that lives in an isolated network. But that doesn't mean that somebody didn't sneak in a thumb drive or bring in an infected laptop. So I'm going to do continuous monitoring and see, is there a threat on there that might not pop up very quickly or something that an IT system might miss? Getting an X-ray view into those systems is what we allow, because they have those systems deployed on-prem, but they don't get to go see what's happening on those networks unless they physically go look at those terminals. So we're allowing the opportunity to get that data out and into the larger enterprise SIM so that they can know what's happening at these air gap networks without introducing risk. Now it's demo day, so I'm doing a quick demo of how you set up some of our hardware here. And we worked really hard to make it a really easy to set up solution here. And the sort of thing where, during the pandemic, we had to sort of pivot and say, hey, we're not going to be doing a lot of installations. Nobody wants to see us. But what it turned into is an interface that you could set up in as little as a minute to get streams of data from one network to another. In this case, we're talking about UDP, and that can be streams of data in file format. It can be video, it can be audio. But I mean, it's really just a matter of picking an IP address and a port, and all of a sudden you can send any number of types of data across the diode. And most of our customers are doing this themselves. It's a drop ship. You plug it in, you get the data from point A to point B, whether that's text or, again, something more complex. But if you do need something a little more even more friendly than that, like you might have data loggers from systems on site. They could be creating CSVs. They could be creating other types of reports. The ability to send that out without having to change those systems, our diode allows for an FTP setup without any additional equipment. So you can get that data shown here. Just select the different mode. You can log in and have that client-server relationship on both ends. You can stream the files, you can buffer them on the device, and you can send it off whether to the cloud or another room in your infrastructure. in that physically enforced one-way fashion. No more burning DVDs, no more shipping hard drives around the world. It makes it a really powerful way to get data out of these systems. It turns it really into a very modular approach. I might have a manufacturer of data collection system A with our data diodes, and then any number of cloud services to help make sense of that data. And so some of those use cases, again, for MEA, they really cared about that one-way sharing of information without sharing cyber threats because they were part of a power pool. They need to share information with their neighbors to help make sure that there is the right amount of energy on the grid at any given time. And they're able to do that by sharing what's going on without sharing network access. We talked a bit about database replication. But it's that insider threat detection on air-gapped networks where you are sending the log files through our hardware or sending alerts that are from those on-prem systems that makes this a solution that could really be deployed at every generation facility, at every substation, and beyond that, every factory and even some government applications. Being able to know what's happening from a cybersecurity perspective in air-gapped networks, regardless of how you're going to analyze it, it's a matter of getting the data you need to do that. And it's a sort of approach that can be deployed today with today's technology and make a difference right away. And the last couple things here, we wanted to make sure that as we go big, that we're working with the folks that become our allies and rather not roadblocks. And so these are a couple of the examples of the people, the organizations we spoke with during our first phase of the project, like ABB. We talk about the big OEMs. You want to make sure that they're on board. They don't see new technology as a threat, but rather an asset so that they can get more life and more data and potentially sell more services with that existing legacy infrastructure. And so ABB's been very supportive. They have a letter of support for our phase 2 application, and we'd love to do more work with their testing lab and do more direct integrations with their technology because they're in thousands upon thousands of substations around the world and in many other places. But then also, working with the regulators, working with the policymakers. We've learned from our conversations with folks like the Virginia Department of Energy, it doesn't matter how good a new technology is, if the legislative environment, if the regulatory environment, even if the policies and cybersecurity standards don't align with what you're doing, at best, nobody is able to figure out that you're an option. You might be a compliance path, but they may not know about you. And at worst, you may actually be written out of being able to deploy. So we're working very closely with these sorts of stakeholders, and we want to expand that in the second phase. But really, the big opportunity is to safely unlock the cloud and AI for systems that really have no business being on the internet in the first place, and having a hybrid approach to getting that data out of energy infrastructure and using the best tools of today and tomorrow while still keeping a human in the loop. Tell them where they need to be, what tool they need to bring, but don't hand over the keys to AI. AI is just not quite ready, and it might be a couple more decades before we can trust our infrastructure to it. So with that, I want to thank you and open it up to any questions.
Great. Thank you so much, Colin. Appreciate that. Robert, do you want to go ahead and kick us off?
Sure. Of course, I have a couple questions on the technology itself supported, but I think the bigger question I have here is, am I understanding that the big drive here is decosting data diode technology, which has existed and has existed in the power industry for a while? Is the main innovation here decosting that for lower income and smaller utilities to be able to use, or is there some other side of the technology that I haven't seen here, didn't capture?
So if you think about, really every technical challenge, it can be turned into a cost. So it's decosting at many different levels. And, one is the hardware itself. These retail for up to a 20th of what you might typically have a data diode that's selling into a nuclear plant. And actually, we're in nuclear plants now where they might already be a consumer of legacy data diodes at the reactor. But we have a customer, for example, in Texas, they had pipes freeze, and now all of a sudden they need to keep an eye on the heat trace. Well, to put in 18 different data diodes around the site. They just couldn't afford it, even though you think it's a nuclear plant. They can spend whatever they want on cyber, which we found is not the case, but they can afford to put our stuff in. But additional factors there with the costing is that it's got a small form factor, and you can clip these into equipment cabinets, and you don't need to build additional infrastructure to do that. They're also easy to install. It's not a command line. It's not a bespoke engineering project. You could have these things up and running very quickly. And on top of that, compared to things like firewalls, where the patches and updates, it's really if you're completely on top of your patches, it's still an arms race for second place. The bad guys are always going to be a step ahead. And so when it comes to making sure that I'm still protected as a utility, even if I didn't do my cyber diligence today, it continues to protect you even if you had other fires to put out. It's that permanent one-way thing that makes it both more cost effective, but easier to use. And these things all do come down to ways that make it just simpler to deploy. And in fact, with the co-ops, we have several co-op customers now. They're often sharing an IT or a cyber professional with 3 other co-ops and the local government. So it's a matter of making sure that it's easy and accessible.
Okay. And the only other question I'm taking a look at, I've noticed just on the public information about these particular devices, you support Modbus, BACnet, and LAN IP. Are there plans to expand that to the more common protocols used by power industry, such as DNP3 and ICCP?
Those are on our roadmap, and so those are some of those that could be as early as the end of next year. It's the sort of thing where, because it's a diode and we can't do remote patches and updates, we take a really conservative approach to testing. So it's sometimes, actually often the testing takes longer than the development because we want to make sure it's rock solid. But those are on our roadmap. There's some others as well that are a little more IT focused, but we expand the protocol list. We go out, we find more customers that needed that, and then we continue to grow from there.
Okay, thank you.
Thank you.
Yeah, thanks, Robert. Sarah?
Hey, one of the questions that I had from the looking over the written documentation I had sent in was around your vision for how clients will interact with the data that they then receive, right? So is the vision that another data diode needs to go the opposite direction in order for them to remotely interact with some of these alarms that are coming in to them? Or is that then the point when they need to deploy physical personnel to the site to attempt to understand and mitigate the alarm that has come in?
That's a great question. So there's in the world that we're living in, we're often replacing an air gap in the first place. So being able to have that data come out in a one-way fashion and then inform that truck roll or the avoidance of that truck roll is something that our customers today are really comfortable with. And some of them, a truck roll to the next substation in an electric cooperative, it could be, a 3-hour round trip. We're talking big time savings when some of the times people call us because they don't have enough personnel. We're about making their labor costs, make sure that they can get the job done with the same number of people as folks are retiring. They're not coming into the workforce. There are some customers that have one diode out and another diode in. Generally, they're different streams. The diode out, you're not going to be able to penetrate back in. And the diode that's going in, you can control where that data is going, but you can't reach in through the diode and do lateral movement because you're not seeing what's going on back there. It's a little bit more of a complex implementation, not actually to do, but to sell. And so from a messaging perspective, it's just keep bad guys out, keep good guys out, everybody out. And we find enough customers who like that because it keeps it simple. However, there are other times, like we're working with some big energy storage battery installations, where one of the major manufacturers, they do things their own way. There's no getting in their way. And some of the government customers, like military bases, like, okay, manage your batteries however you want. Please don't get us killed. But we really need to know what's happening. And so that's a use case where we're using the hardware to siphon off that data to the customer or the end user so that they get visibility into what's happening, but they don't actually get to control it. And we see that in building automation systems as well. So it's an opportunity. Actually, data centers has been a big market for that. The data center operators do not want somebody penetrating that network. But the people who do the cooling for the data centers, well, they can't meet their warranties. They can't do their SLAs if they can't get the data. And so we're doing that with some of the major cooling vendors there. We're doing that with GE turbines and some utility applications where you get to keep your GE warranty if GE gets the data, but they don't need to control.
Cool. Thank you.
Thank you.
Thanks, Sarah. Jody, it looks like you have your hand raised.
Yeah, hey, well, this is interesting. However, I feel like we've almost lost the bubble on the cybersecurity aspect. I get what you're saying, but the talk keeps going back to data flow and one-way data flow. And this is not a replacement for IDS. So my question is it, the compatibility with IDS? Does not do real-time detect and mitigate. So it's interesting that people can get the data, but something still has to be done with it. It's got to be analyzed. It's got to be actioned. So I guess my big question here is, like, can you explain concisely how this actually, interacts with cybersecurity solutions that people normally have, right? Because this in and of itself is not a cybersecurity solution. But how does it, how can it enhance that interaction? How can it improve that real-time detection? Especially as we go away from air gap situations. I mean, the trend is we're moving away from that. We're a distributed energy network now. We're not, moving backwards to more air gap. So just curious on that note, just to bring it back sort of to the overarching cybersecurity theme. Thanks.
So this hardware is not a scanning tool, though there are future iterations of this where you could be running scanning tools on it. It is an enabling technology, and whereas some of those IT security scanning technologies have been around for decades, they have been out of reach for a lot of the energy industry. There are parts of the industry where you have to use a technology like a data diode, or you have to use an air gap. You aren't allowed to make those sorts of connections. And so this allows for those customers to get that delivery. They may be excellent chefs and there might be great food over there, but if you can't get those groceries into these chefs' hands, nothing can be made. And we're really in the data delivery business to enable those utility customers to use some of the best tools on the market. It's a mature space in many ways on the cybersecurity side. You've got some big public companies like Tenable, for example. You've got the Dragoses of the world. You've got Clarity. And we work well with those sorts of tools, but we got advice during our SBIR project with the EERE, the Solar Energy Technologies Office. Don't go spend your money trying to be another analytics company when there's a market need here to help connect these systems. So that's really our role. I will say, even though the world seems to be moving in a more connected fashion, there's enough fear out there. I mean, we've done the best year of business we've ever had because people are losing their minds over AI. Because the good guy AI seems to do as much bad as the bad damage as the bad guy AI today. So it's really, I think we're going to see a more conservative approach to cyber out of this space for a lot longer than we think. And we're here to meet those teams where they are.
Great, Colin. Thank you so much. Looks like we're right at time. So if there were any other questions, feel free to send them over to me or the Digitizing Utilities inbox. But thank you so much for being here. We really appreciate it.
Thanks, everyone, for the opportunity.
All right, looks like we have two more people that are switching over to panelists right now. You just give them 1 second.
Hello, can you hear me?
Hi there, Brian. Yes, we can hear you.
Great, and Nate's on too. Okay, great.
Hey, Nate.
Yeah, 1 second. I should be unmuted. Can everybody hear me?
Yeah.
Gotcha.
Okay, good.
Carly, one question. When we get to the panel portion, I have some other folks. We have a kind of a cast of heroes. So can I give you names, or how do we do that?
We did have to limit it to 2 people if one of you to jump
Okay.
off, if that would be best.
Okay.
But you have the option if anyone wants to drop anything in the Q&A. We'll also save all of these questions and send them out to you guys so that you can answer them, and then the answer will be posted into HeroX to make sure that we cover everything that the panelists had and then anything else that comes up.
Oh, okay, great. Well, yeah, I might drop off at that point. So, but let's get going. So, let me figure out how to share my screen. Share. Let me share this one. Share sound. All right. Can you see my screen, I hope?
Yes.
Okay, great. All right. Asking for some permission stuff. All right. Here we go. Hello, I'm Brian Bassett with SimpleThread. I'm presenting today with Nathan Rice from Dominion Energy, and alongside our power systems partners, Right Analytics, we've developed digitizing our submission for digitizing utilities, Graph the Grid. There we go. So as mentioned, Right Analytics and SimpleThread partner to address this real-world challenge with Dominion Energy. Dominion is an IOU with 6,000 miles of transmission lines, and they had a 2023 summer peak of 21,900 plus megawatts in Virginia. And the goal here of what we're trying to accomplish is to create a scalable software application to redefine how to approach transmission scale, hosting capacity analysis, initially from a large load study perspective, a problem that Dominion uniquely has among many utilities, but many other utilities are starting to see this same challenge. So yeah, like just to quickly explain some of the bottlenecks and pain points that Dominion has experienced over the last couple of years and would have without this application. This is a very time-intensive manual process to do one study for one potential load point. It could take a principal, senior, super senior, expert level engineer up to 1 month to do one study. So sometimes when people are coming and they're looking at multiple locations, that makes it a lot more challenging. It also impacts the rest of the special studies teams who would be working on other work. If someone catches a case, as it were, for this, that takes them out of the rotation for all the other work. So this is a real problem for utilities and is going to continue to be a problem for not just one utility, but all utilities as large load ramps up. The problem is running this stuff on laptops, which is the traditional method, doesn't work. So just taking this and putting it into a distributed platform has certainly seen lots of improvement for the team, but it's also afforded some other gains, which we'll talk about a little later. But just getting it off the laptop, being able to run a study on a whole area as opposed to a subsection, a zone, that sort of thing has been really impactful. Nate, I know you're there. Any thoughts specifically in terms of the pain that your team sees?
No, one thing in particular is that we're seeing it spread out more than just Northern Virginia. That's, typically been the largest data center pocket. But we're seeing more and more counties getting involved. So being able to quickly analyze the capacity in different areas has also been, or is also a huge gain.
Great. So here's a typical process of what a large load request might look like. This could be really for any utility. This is just kind of more, how does this apply across the US? So with a surging load, a large load, commercial and industrial demand that's growing exponentially. Nate mentioned specifically data centers, but that it could be electrification, it could be manufacturing, could be battery, people building battery factories, whatever it is. They will come in and you can kind of see the process on the right there. And there's a pre-application process, there's some consultation and discussion, but ultimately it comes down to the studies, and the studies, like, that's the real bottleneck in this process. Different types of studies, system impact studies, feasibility studies. But this is really the initial version of that. How do we look across the grid and find places where where there is capacity available before we're really digging deep. But even those initial studies could be really painful. So this is our solution here. As you can see on the screen, there's some screenshots of the application, hosting capacity analysis, HCA, as we call it sometimes, or hosting capacity. These are screenshots of what the study process looks like as someone goes through this. We'll see this a little bit more in a minute with the demo. But basically, this is deployed on distributed servers. The software can scale. It basically enables engineers to make accurate decisions much more quickly than they've ever been able to before. And you can see some of the innovations. I mean, these are not innovations, these are typical things, but to do this in a process that could take hours as opposed to weeks of N-1 or N-1 or other N-1 or other contingencies, and then also afford some examples of what this is going to look like, visualizations of that. So how do we validate this? You can see here, I'm not going to go through all of this. It's kind of an eye chart, but this is Right Analytics superpower, and they went through this with this team. You can see the steps on the right of kind of what the process looked like. Effectively, think about, we're trying to build this software and put the intelligence into the software, but at the same time, we have to ensure that whatever comes out of that automated process is explainable, is transparent, but it also is accurate. We're not going to go fast and go incorrectly. We got to go fast and correctly. So there was a lot of time spent kind of parallelizing those studies between the manual process and what it would look like in the app to make sure that we're getting accurate results every time. And so some of the feedback from one of the engineers who would use this tool said it exceeds expectations, and just is very excited about it.
Hello.
Sorry.
My name is Nick.
Okay, so hopefully you can hear this. Here's the product demo. Here's how it works. Nick from our team is going to run this through. So, all right, I'll start it off.
Giuliano, and I'm a senior software engineer at SimpleThread, an energy-focused software consultancy that's based out of Richmond, Virginia. Let me introduce the application we'll be exploring. You've been looking at it already. This is hosting capacity analysis, sometimes shortened to hosting capacity or HCA. Our partner, Dominion Energy, came to us to develop this application, and they had a pretty clear problem. There's a certain type of study that they would run in order to find what we call hosting capacity for certain geographic regions. In other words, is there enough capacity that we could service another large load customer in this region or county? They had a process for running these studies. The problem was that it took too long, and it was a pretty manual process. So that's what the application does. Instead of having to run the studies on their own laptops, which would take upwards of a few weeks to maybe even over a month, they could send requests on a web application, and all of the background work would run on servers off of their laptop. So by breaking the studies up in a way that they could be run distributed across many high-powered servers, we were able to get the study time down from a few weeks to maybe a month or more down to just a few hours. So this page we've been looking at is the study request overview page. When a user requests a study, if there's already one running, theirs will be queued and it will show up here. So it also has very basic searching in case there were many studies in the queue and you wanted to find a certain one. There's a similar page, the study archive, which is all of the studies that have finished, which has the same searching and filtering. Now let's create a new study. Studies have to have a name, a study type, which can be line tapping, bus tapping, or both. For the most comprehensive study, we're going to choose both, and we're going to do a full area study. You can also do a smaller region or a single zone, and you can choose different contingency scenarios, but for the most comprehensive, we'll stick with this one. Users are required to upload a couple of input files. These are snapshots of the grid at certain points in time, as well as a couple of contingency files. Once all the inputs are set, we can go ahead and run the study. Once our study is created, we land on the details page. This is where we can check the status and any progress that has been made. If we check back, we might see that a certain number of lines or buses have been completed. And checking back one more time, now the study is completed. Once the study is complete, the users can navigate to the results folder to inspect the various outputs. Most of these are in the form of CSVs, but we also generate a few map images. When Dominion Energy came to us with the idea for this application, They had a lot of issues with how slow it was running, but also all of the manual processing that they had to do at the end of the study. So the nice thing about this is that all of the map building is being done automatically without user intervention.
All right, thanks, Nick. So let me see if I can. There we go. Oh boy. Sorry, I need to get it back to full screen, but we'll just keep rolling.
Hello.
Oh no, I did it. All right. So basically, as you can see, that's the application, and obviously, all this data is not real data. We're kind of populating dummy data for the purposes of this, but this is live in production and works. So just to show some of the milestones that we had set forward at the beginning, in the kind of back in the spring when we talked about this, trying to just show here, hey, here's some of the things that we've been able to accomplish in that time. So some of it's very basic stuff, cross zone lines, but also things around SCRD and mitigation cost. Obviously, there's lots more to do. We did as much as we could. We obviously had to go through a prioritization function just to make sure we were, delivering on this and kind of, what we could accomplish in this time frame. But I think we're pretty proud of the results that we've found so far. So Nate, do you want to talk a little bit about kind of how this is, how your team's using it, or what impact it's had so far?
Hey,
Yeah,
Brian,
so it's
you only have about 20 seconds left,
Oh,
so sorry.
really?
Oh.
What?
Yeah, for your presentation
Oh
time.
gosh. Okay.
Um,
All right.
So maybe it's something that we could cover through questions, or if there's anything else, or if there's maybe a slide you'd like to throw up.
Yeah, absolutely. So one of the important things I do want to say here is that this is something that it's not just for the super wizards study engineers. This is something that's going to condense their work and make it shorter, but it's also something that can be socialized across more staff level engineers, which we're very excited about. And so that means, yes, this can work for a large load, but it can also work for all sorts of other applications and uses and make that process a lot less painful for teams. So just kind of as we go forward, this has basically made a major impact for them. So we're very thankful for the opportunity here to talk and share the results here. There is a surging demand in large load requests, and it's going to hit across the entire nation. And we know Dominion is really at the forefront in this. So we've been really fortunate to partner with them in this. So thank you. Thanks for listening to this. Thanks for the opportunity to share.
Great, thanks, Brian. Sorry to cut you off there.
Mhm.
Just want to make sure we have enough time to get through some questions. Feel free to let me know if there's anyone you'd like to.
Yeah, I think it would just certainly depend on the question. So I might kind of play quarterback on that. But I would say Saman, maybe if Saman can hop on, that would be helpful.
Okay.
Can we have him, or do you need me to pop off?
I will have to kick you out if that's all right.
Okay, that's fine. Why don't you raise up Saman and I'll pop off at this point.
Okay, thanks so much, Brian.
Mhm.
Were there any questions from our panelists that we wanted to kick off? We did shave off about 2 minutes of time, so just wanted to be aware of that. Andrew, go ahead.
Yes, hi. Thanks for the presentation. Hosting capacity analysis is very important. But on the other hand, so my specialty is in optimization in power systems. And you mentioned about improving the solving time for N-1 security constraint, like increase 1,000 times or something. How did you achieve that? From my perspective, it seems like you simply just moved the running from laptops to servers. Is that all you did?
Is Brian on, or Saman, are you a panelist?
I think we might be switching over.
Ah, there's Saman.
Yeah, hello everybody. Unfortunately, I didn't hear the question because when I was switching from audience to the panelists, I got disconnected, so I could not hear the question. If you could please repeat it.
Sure. My question is, how did you achieve the much increased solving time for the N-1 or N-1 analysis? My understanding is you're simply just moving the computation from a laptop to servers. Is that all you did?
Oh, okay. Now I understand the question. Yeah, there are two things that we have done to improve the processing time. One is, like you said, working, going from the laptop to a server and using multiple core. But the other thing that we have done is using different power system algorithm, right? So for running n-1 and n-1 contingency analysis, instead of running contingency analysis and do like an iterative method, put a load, run contingency analysis to see whether there is a thermal violation, increase the load again, and run the contingency analysis. Instead of doing that, we have used thermal transfer limit analysis, which is doing this in whole one shot. So essentially, instead of running contingency analysis, we have run thermal transfer limit analysis. And for doing thermal transfer limit analysis, we have used the thermal transfer limit module of Tara, which is a software which is being used by all the utilities, by many of the system operators, and the results are completely FERC compliant. So this is another innovation that we have used. Like I said, instead of running an iterative method, contingency analysis, adding the load, we have used thermal transfer limit analysis.
Okay, and that's from your company, right? It's not from another vendor or?
No, I mean, thermal transfer limit analysis is a very known methodology for calculating hosting capacity analysis. What we have developed is the automation code. So we have developed an automation code to understand when we are running thermal transfer limit analysis, what should be the definition of the sink and source subsystems, what are the how we have to set the parameters. But the engine for running thermal transfer limit analysis, like I said, is Tara, which is a software that all the utilities, all the system operators are using, and we have used their engine essentially. We have not developed the engine for running thermal transfer limit analysis. We have just written the automation code.
Thank you.
Sure.
Perfect. Looks like we have one more hand raised.
Hello, very interesting work on capacity analysis. I understand how you are increasing the efficiency and reducing the computation of time you doing this analysis. In proposal, you also mentioned improving accuracy. I'm wondering how with your method you also improve accuracy.
Yeah, I can answer that question. So yeah, the way that we are increasing or improving the accuracy of the result is that we have added a couple of other modules to do this load hosting capacity analysis. So traditionally, when it comes to running load hosting capacity analysis, people are running contingency analysis or thermal transfer limit analysis. Not only we have done that, but we have added some other modules like HCRD analysis, like thermal mitigation cost calculation analysis, and a couple of other modules. So for an example, just to give you an example, for the HCRD analysis, in our thermal transfer limit analysis or contingency analysis, we are also looking at what would be the impact of redispatching the generation units on the thermal violations, right? So if there is a contingency which is creating some thermal limit in our system, would it be possible to redispatch the generator and get rid of that thermal violation? This is something that we have also done, and we have added to our platform, the tool that we have developed. So by adding these more modules, essentially we are looking at different dispatch of the generators instead of just looking at one dispatch of the generation units. And that's why we are saying that we have improved the accuracy of the results.
I see. Thank you.
Sure.
Maine, go ahead.
Hi, just out of curiosity, does this planning consider, you know, like the future load forecast, renewable generation forecast, and what is the planning horizon of this?
Yeah, Meng, this is a very good question, and that was one of the very important aspect of designing this tool from the very, very first day that we started to work on this project. So what would be the time horizon of this tool? Is it going to consider all the new loads that will be added to the system? Is it going to consider all the new generation resources that will be added to the system. So the way that we have approached this problem, we have considered this problem, is that the tool that we have developed is 100% model independent. It means that you can use whatever PSSC model, FERC compliant model that you want. The tool is going to run some screening to understand what model is, what are the transmission lines, what are the name of the buses, and then goes and start running load hosting capacity analysis. By doing this, essentially, you can input whatever model that you would like to have. You can input the FERC compliant 5-year out transmission planning model, FERC compliant 10 years out transmission planning model, or the interconnection queue model, or whatever model. You can even manipulate your model, do whatever, add whatever load that you want to have in that model, input it to the tool, and the tool is going to run all the hosting capacity analysis.
Thank you.
Sure.
All right, well, we're right at about time. So if there were any additional questions, feel free to send them over to us. But we really appreciate your time and your flexibility with the different panelists and attendee settings. We appreciate it.
Thank you, everyone.
Thank you. All right, it looks like we should have Jason on the line.
Just tell me when to go.
All right, hi, Jason. We can see your screen and you're coming in clear. So whenever you're ready, I'll start your timer.
Okay, 1 second. Begin. Hi, everyone. My name is Jason Traeger. I'm the CEO at Plentiful AI. Our utility partner was Portland General Electric. Just the quickest introduction about me. My history is PhD in mechanical engineering at Berkeley, focused on using large-scale machine learning and time series to predict efficiency in buildings. Went through that doing like data-driven storytelling in a consultancy in the energy space, and then eventually landed in using geospatial machine learning to automate forecasts and utilities. And that brings us to Plentiful. There's a lot on these slides, and we have very little time, so I'm going to go through them very quickly. The challenge that we accepted was adopting the improving the pipeline throughput of interconnection applications at the distribution level up to 100 kilowatts. There are multiple sources of inefficiency in this process, including developers, the DER developers not knowing where the capacity could land, and the utility engineers not knowing that they'll get good applications. When we combine these two, we get a systems thinking approach that allows us to essentially bring down the cost of both by automating a lot of the initial analysis steps. So the DER developers and the utility both contributed to least cost grid upgrades in this case. The concept was to provide DER developers with a map where they could see the projects that have been pre-approved and to enable them to use that map in order to claim and register projects where we'll go through automation on back end in order to go through PG&E's system. During this phase, we had the fun experience that a week after we got the prize, our utility champion left, and it took us about 10 weeks to get rolling with a new person, all while I was developing like the back end code that we would need. So during the progress phase, we integrated data from our app into our PG&E's backend. We developed a simple functional app, which I will demo for you shortly. We created savings estimates. We built in interconnection rules. We built a machine learning to validate parts of the application, which is a bonus. And then the PG is currently validating the application because you don't want to rush these things. And we're planning to launch the system fully after testing and UI refinements. Okay, we have a demo. Can you see my screen? Okay, I see a head nodding. So this is a map of every multifamily building in Portland. And what we've done is we've mapped up to 20 level 2 chargers and 2 fast chargers for every building. And what we can do here is we can enter economic assumptions and click on a building to come up with like the possible registration capacities. Enter the installer name, upload a contract, upload site plan, and register the project. But what's really exciting to me is letting the developers actively filter the projects. Let's say I want to install, I don't know, 6 to 8 chargers. Then we can choose these apartments, and for the sake of speed, everyone's going to have a 1-letter name. I should have pre-filled this. We can then upload a contract, which for purposes of this demo, it's just a picture of colors. And if we want to apply, the contract uploading will reserve the project, and it's sent for registration. And then on the back end, you know, if you ask me a question about the API, I'll show you. I want to get through everything. There's an API call to Portland General's backend registration processes. So it's kind of a simple demo because we want the process to be simple. We're simplifying a whole big piece of software. So from there, there's a lot of stuff in the back end happening here to make this front end simple. One of the things that's happening is that we want to actually go through the contract. This is, you can see here, text that was scanned in on the, like from the 1-line diagram and the site plan. And what we do is we go through, we validate that like what was entered in the application matches what we can see from OCR on that's optical character recognition. It's machine learning that recognizes characters. We see that they have applied with. We then can go through the site plan and we use edge detection, and then some analysis to count the number of panels. We can count the number of inverters through like some text analysis that's still underway. And where this leaves us is being able to automatically confirm a lot of steps in the application process that aren't confirmed mathematically through the rules-based transformer analysis. So yes, that is everything on that slide. So the solution is being evaluated by the utility in preparation for integration into production environments. We need to refine the process flow further. We need to really validate the machine learning. We haven't had many sample sizes, a large sample size to do that on. And we actually are discussing commercial terms, which we think is a really good signal that it's going to go past the demonstration, like prize phase, and move on to commercial adoption, as well as being applicable to other utilities, who we started to talk to when we submitted one of their letters in our application. I don't think I need to say that there needs to be UI refinements. You saw the demo. So the impact of this is that interconnection is a rate limiting step for both transmission and distribution. Transmission and distribution installations of DERs. We initially calculated that we're going to chop off 25% of the time that an engineer spends doing like an interconnection at Portland General. And we're also going to improve the rejection rate. And later we found that once we started doing the machine learning, OCR and other tooling, that we're going to reduce it by another 25 to 40% because we're automating essentially the whole fast track process. In addition, we're going to reduce the rate of equipment replacement, specifically transformers, which is critical because of the long lead times of transformers all along the scale in utilities right now, anywhere from 8 weeks at the bottom for pole-mounted transformers through more than 150 weeks for a large-scale transformer. And I will note that a lot of these applications are moving to pad mount transformers, which have a high lead time. Additionally, placement is critical. This is a analysis showing that where our models calculated the amount of EV chargers that could go on the individual buildings, if we aren't careful with the adoption rate across buildings, and the maximum adoption is the maximum technical potential, so we're not going to do that, then way more of our transformers will become overloaded. However, if we steer towards the transformers with more capacity, we're going to get significantly better results. We're going to have less overloading, and the developers and the utility will have less cost, and there'll be less lead time, and we will approach a least cost optimization for the development of projects. In addition, we're going to be applying to a upcoming DOE grant, and this project has prepped us for it. We've developed the AI-driven backend for doing interconnection, and that is it. And I will just briefly show you. I can't zoom in here because of NDA things, but all of these blue boxes are those that we set out to automate. And what we did not achieve was one loop that is essentially a manual review right now that we're in the process of automating with machine learning. That's my time.
Great, thank you so much. Appreciate that presentation, Jason. Are there any initial questions for our panelists before we jump to anything that Jim might have? Jim, I don't
started. So you talked about the 25% reduction. Can you put
Yes.
that in terms of time?
So, and I might have missed my unit in the written application. I might have said weeks instead of I might have said days instead of weeks. So I can't put it in time. I can put it in throughput. Well, I guess it's time. So the PGE does 150 to 200 applications a week, right? And so we're going to increase that by 25%. So up to 250 applications per week. Now, in dollar savings, it's going to be around $250,000 in savings per year.
Where do the financial savings come from?
I took an average salary of a Portland general engineer off a Glassdoor and multiplied by the 25% and multiplied by the number of folks on the team. So there's a little bit of estimating because I didn't want to ask how much I got paid.
There's one of our reviewers had a good question about in pre-approving these interconnections, are you studying them all in isolation, or are you able to study sets? So you've got two apartment buildings next to each other.
Yes. So what we do is we have a GIS layer that the utility doesn't want to expose to the public, but is all right with us connecting to, of the transformers and the distribution lines, like the shared lines off the transformer. And so what we do is we go through the whole thing. We essentially study the whole thing at once. It only works for applications under 100 kilowatt hours, under 100 kilowatts. Excuse me, that's embarrassing. Because fast track rules work there. So in essence, we study the whole area at once. We then reserve spots by application time in, and therefore we have to update it as each application is approved so that the entire map is updated, but it takes a few minutes to update.
There's another good question about so how did you validate that the approval that your tool is automating is exactly the same as what would be approved if it was an engineer doing every part of the study? Like,
Yeah.
How do you are you certain that you're not being overly conservative in that?
The approvals for these size systems at this utility are a decision tree largely. So what we do is we go down the decision tree, which is presented on this screen, which is essentially like what size is it? Does the transformer have capacity? Apply power factor. I mean, apply like some power flow calculation against the transformer, and then go through a few other rules to figure out if it's fast trackable. If it's not, and we can't approve it according to the rules, or we can't approve it according to the rules, we kick it to this box here, which is the normal process. So we had the team validate the rules. We wrote tests for the rules, and we're doing a third check because, you know, utility engineers like to do that.
I'll turn it over to Fernando.
Yeah.
I don't know if this was captured, sorry, in and out, but what percentage of the studies can go and be validated through your process compared to like ones that are like more unique and studies? I've done studies before. Sometimes it does take a human factor to be able to change or make some judgment calls for certain things. But what percentage of the total amount you think it can be covered by this process?
98%.
98%. All right. And then would this be just for PG&E or also other I'm thinking this is only for distribution, but other distribution process, because there are level 1, level 2, level 3, level 4s in some areas. Would that also be applicable for other utilities?
Yes. And in fact, like we integrated with Power Clerk, which is building an integration with their API, which is an application that's used as a system of record across many utilities. There will be other rules, and other utilities will have to get there and adapt them. But the back end, the like GIS backend and automation is there, and will also enable us to move up the line to distribution. I mean transmission projects, where more than 70% of projects of applications are deficient according to LBNL. Purely because the application was wrong in a manner that a AI-enabled GIS backend can determine. So we can kick back 70% of applications at that level when we move up there.
Oh, okay. And this final one, this will also have to, how do you process kind of like, you know, that interaction with the customer? Because sometimes you need to go and get more detailed information from the customer. Would that be done by just the engineer and then put it back over here? Or and then would this would your process flag certain things like that when
Yes.
you have any? Okay.
It won't be our job to like automate that interaction with the customer yet,
Yeah. Okay.
because we don't want to bite off more than we can chew. It goes in the Power Clerk. They have a normal process. They can kick it back.
Okay. Thank you.
Jim, I think that was our only hand raised for now.
One more from one of our reviewers was they noted just how, you know, your tool of course depends on a lot of GIS data from the utility, and I imagine as part of the normal process when they're looking at that information on a case-by-case basis, then they're having an opportunity to review that. So can you talk about the data preparation that's needed for your tool, especially given automation and where you're looking at the whole system all at once?
Yeah, so the hardest thing to confirm is that the lines and the points go where they actually go, meaning that the specific circuits and the specific transformers are connected, because often the circuit level diagrams are messy, and this is consistent across utilities. And so we ingest the like input data from the user and treat it as the truth around certain validations, and are coding more so that they can't like enter a string where there should be an int. Simple like example. On the data side from the utility, like actually one of the challenges right now is that a lot of those data points are manually drawn. So every time the engineer needs to confirm a point, they need to go look it up. And so we are drawing that in automatically. So our system actually draws what's from their database. And on the validation side, we flag points that don't seem to be connecting correctly, that like don't seem to go to the building. And then we also go through and kick back data that doesn't seem to fit, which is something that we're still working on. So long story short, we validate GIS data. We assume the customer entered correct data unless it's, you know, the wrong data type. And I really think it's going to be an ongoing process. Like they're not going to trust the entire thing all right away. Like we'll scale.
Thank you.
Great. I think we have just about one more minute. If there were any other questions, I think that was all that Jim had.
If you don't ask a question, I'm going to tell a bad power systems joke.
Always options. All right, I think that was it from our panelists. Jason, we really appreciate your time today in answering all the questions for us. Thanks for being here.
I appreciate all of your time and thank you for the intelligent questions.
All right, it looks like Daniel should be on the line next to start his presentation. Daniel, can you let us know if you can hear us?
Yes, I can hear you. Can you hear me?
Can.
Excellent, and I should be sharing my screen.
Yep, we can see your screen.
Great. Howdy, everybody. My name is Daniel Ressler. I'm the founder and Chief Innovation Officer at Utility API. We are a software vendor for utilities and third-party entities across the country and Canada, providing data access services and data access platforms for utilities. Today, we are talking about the project that we have with Silicon Valley Clean Energy, SVCE, in the Bay Area in California, and how we are working to standardize connectivity between vendors and utilities. And so as for this presentation, we're going to go through some background. We're going to talk about the project scope itself, talk about the phase 1 results. I'm going to give a demo of the demo platform that we developed as part of the phase 1 system. And then we're going to talk about phase 2. So as a little bit of background, so Silicon Valley Clean Energy is a community choice aggregator. They're a CCA servicing hundreds of thousands of customers in the Bay Area, in places like Mountain View. And they launched a portal, a data access portal called Data Hive in early 2020. And that serves the purpose of providing secure customer authorized data access to third-party entities. So think energy efficiency contractors or program implementers. That system was Utility API hosts and manages that system for Silicon Valley Clean Energy. It currently relies on the Green Button Connect My Data protocols, which are a set of standardized protocols. It has been certified by the Green Button Alliance, and this is a screenshot of the homepage there. And it's been used thousands of times to share data. So it's a relatively robust platform that's been around for many years. However, it has some significant limitations that we are looking to improve with a new set of specifications. Speaking of that new set of specifications, the Linux Foundation Energy several years ago launched an initiative called the Carbon Data Specification Consortium, primarily focused on addressing the needs of carbon accounting platforms. So think of the SEC calculations for carbon impact, that sort of thing for companies. However, the specifications developed by this, and Utility API is a maintainer for some of the working groups within that consortium. They're really developing next generation APIs that utilities can use to offer standardized connectivity and access to customer data. But primarily we're focused on the connectivity of these connectivity specifications in this part. Large companies support these initiatives, and they're active members in the working group. And this is a screenshot of one of the working groups' homepages. These specifications are completely open and freely available. That's one of the benefits that the Linux Foundation kind of brings to this, is that these are open specifications that people can see, and they're on track to go to ISO to get an ISO designation as well. So as a little bit about the project scope, this is the current state of the data hive infrastructure at Silicon Valley Clean Energy. On the left side of the diagram, we see the SVCE backend. So that's their data warehouse, their data vendors, that sort of thing, where all of the meter data goes, where the billing information is. And then SVCE Data Hive is the front-end platform that's hosted by Utility API. And that has a set of APIs associated with it called Green Button. Those are the Green Button APIs. And then the third-party vendors, so think of the energy efficiency contractors or the virtual power plant analysis tools, the commercial and industrial consultants, that sort of thing, the EV infrastructure providers. They're all kind of hitting those APIs to get customer data. And that platform does include the process of getting customer consent when needed for a particular third party who needs to get customer consent in order to get their data. Okay, so that's the current state. And what we're proposing, or what we are studying in this project, is how feasible is it? What is the level of effort to add these new open specifications from the CDSC to the Data Hive platform? And so there are two major aspects of that. The first one is the connectivity APIs. And so that's how you actually register with or find out what sort of capabilities the Data Hive has. And then the second part is a new set of modernized API endpoints for getting that customer data. And so one of the important things about the first part, the connectivity specifications and APIs, is that they enable both the existing Green Button layer, which is how third parties get data now, as well as enable the new set of APIs that are more fully featured than the existing Green Button APIs. And that's important because the current Green Button APIs, they don't have any means. It's a manual setup to establish that connectivity, to get your API tokens, to register with Data Hive. And so with these new specifications, we're really kind of automating and enabling scalability of interconnectivity and establishing connectivity with utilities. And what that unlocks is a future state where once you have those connectivity APIs in place, you can enable future protocols, even if they're not specified by the Linux Foundation, even if there's some proprietary protocol or some sort of demand response market-based protocol. Those all generally need some sort of initial connectivity and secrets exchange and registration that can be automated by these new APIs. So that's really the potential for SVCE's Data Hive, as well as other utilities who need to interconnect with external entities. As far as the project scope, the first phase one of the project was to create an implementation study, basically a report that says, hey, what would it take to actually do this? And we have done that as part of this phase one. In addition to that, we have also created a show and tell demo of these specifications as a demonstration, the idea of show, don't tell. And so that's what I'm going to be demoing in just a moment. And then after we have gotten sufficient kind of iterations and feedback, we do plan on publishing either a case study or a blueprint for other utilities who may have this need of being able to scale connection with third-party entities. Okay, so I'm going to go ahead and do the demo now. So this demo is live at cds.utilityapi.com. That's the carbon data specification. Those are the specifications that we have. And here I have the landing page of cds.utilityapi.com. I'm going to go ahead and register as a utility. So this is going to be as if I am a Silicon Valley Clean Energy. Once I have that, I can create a new server. And so server in the specification is basically how you as a utility can offer data to third-party entities. I'm going to go ahead and create that. And what that does is it spins up a new subdomain that is for my specific thing. Now, this is a demo platform, so this is all fake data. This is all kind of like pre-structured data, and we'll get into the phase 2 scope. But as part of this spinning up a new server as a utility, you are automatically given a set of metadata that can be discovered by third parties, and that's part of the API specifications from the CDSC. As part of that, you have a website that third parties can automate integration with. So I'm going to go ahead and open that in a new tab, and this is an example landing page for the server that we just spun up on that subdomain. Now, if I am a third-party entity and I come here and I want to register a new client, which is the nomenclature in the specifications, I can register a new client. You can, as a utility, enable various fields that you want the clients, the third-party clients, to submit as part of their registration. But there's no clients on this default platform, so I'm just going to go ahead and register a client. And all of this is automatable via APIs. As part of that registration, there are several, I guess, client IDs or registrations that are put in place, one of which is by default access to customer data. Now, this is not carte blanche access to all customer data for that utility. This is behind, it uses the OAuth protocol, which is a widely accepted protocol for gaining customer consent. It uses the OAuth protocol to obtain customer consent. So if you want to get customer data, you need their consent. And so I'm going to copy this link, and on the right side, I'm going to act as a customer. So if I want a customer's data, I can send them this link. The first step to authorizing access as a customer is logging in. And so we have some test logins here.
Hey, Daniel, so sorry to cut you off.
Yep.
We're about 30 seconds over. If you have any.
Oh, I'm so sorry. I will go back in. So this is the demonstration. And for phase 2, we are proposing to create a branded and utility-specific implementation of this demonstration platform for the Data Hive so that third parties can present or can try it out. Thank you.
Yes, thanks so much. Sorry to have you wrap up quickly there.
Apologies, my clock was off.
No worries. Just want to make sure we have enough time
Yep.
for Q&A. Is there anything from the panel before we get to Jim's list of potential questions? Andrew, go ahead.
Yes.
Yes, thanks for the demo. I just want to understand a bit better. So the client submitting data, that's completely voluntary, is that right?
So when we say clients here, we are talking about energy efficiency companies, DER companies. They are wanting to register with that utility in order to gain some sort of connection. And so they generally have a use case that they are looking to address. So if I am a solar company and I am working with a building, a commercial building, I want that building's utility bills and usage data in order to do my cost analysis. And this is the data platform that they use in Silicon Valley Clean Energy territory to get automated access to that data.
Okay, so this is not for any real-time operations or analysis. This is really just for, like you said, some analysis like that, right?
So there's three major use cases that this covers. The first is for that initial feasibility analysis.
Right.
You get a dump of historical data, you do your analysis. The second is for the ongoing financial analysis. So on a monthly basis, you basically do a true up of your operations to get like the revenue grade interval data, for example, to assess whether or not you're doing a good job. And then the third we briefly covered, where this connectivity API is a generic connectivity API that not only enables access to the existing kind of usage and billing data on Data Hive, it also, for Silicon Valley Clean Energy, opens up the possibility of scalably connecting real-time or operational APIs like demand response OpenADR or virtual power plant controls. These sort of things need API token exchange, and the CDSC APIs open up that possibility of kind of just adding those features to an existing integration that somebody has.
Okay, thank you.
Yep.
Thank you, Andrew. Were there anything else from the panelists that we'd like to address now? Jim, did you have
This is
questions?
Jim. Can you talk about why the value of open standards versus working through a standards making body, and then what's needed to get the industry on board with an open standard? Sometimes they tend to lean towards things that are known and widely known across industry. So can you address that?
Absolutely. So that's a great question. First off, while this is a open and freely available specification, it is currently in draft form. The Linux Foundation has a history or experience at taking open specifications and then taking them to a standards body like ISO and creating an ISO designation number for that specification. And so that is the pathway that we plan on doing with the carbon data specification, is basically creating this specification in open. It's freely available. Any utility can join. We have many third parties who have contributed to the specifications and given feedback. And there's like regular meetings, and everything's basically on GitHub as far as the sources. And then when it's reached a significant level of stability in the specifications, we can then apply to ISO to get it into a standards body as an official standard. And so that's kind of the pathway that we're doing here. As part of that pathway, we want to have pilot demonstrations, which is what this proposal is, to say, hey, this thing works. This is a proof point that it works, and there are people that would find it useful. So that's another proof point that we're seeking here as part of this. As part of this application.
And that was another thing I wanted to clarify. You talked about this being a proposal. So what you've been doing over the past few months is establishing a plan for something that you intend to do moving forward. If you receive this prize.
Correct in that the proposal is that we have this existing data access system. It has limitations. And as part of that, we are proposing to add these specifications. And we have developed, as part of phase 1, a plan for doing that. And for phase 2, we are looking at doing the next step, which is creating a demonstration branded implementation of that. So basically, these blue parts would be limited to sandbox mode, but they would exist as part of the Data Hive. And then potential future steps in that progress would be enabling it for real customer data. Now, since it's not an ISO number yet, the hesitations on putting real customer data behind these specifications is something that we're still looking into. And so those are the major things we have here. Yes.
Yeah.
Looks like we have one question from the panelists.
Hi, interesting work. I am wondering, other than CCAs, have you guys worked with utility, like the system operators, or do you have any plans or use cases for them?
So utility API, the vendor, my company has mostly worked directly with utilities, both investor-owned utilities, municipal utilities, CCAs. We have also worked with statewide data hubs. So for example, we're working to spin up a data access platform in the state of New York that covers a bunch of utilities. So that's kind of like a regional data hub, which is very applicable to this. We have had discussions within the Linux Foundation, CDSC working groups and conferences with ISOs and DTOs in Europe on the applicability of this for data exchange between ISOs or larger infrastructure providers and their vendors to provide kind of like scalable connectivity with that. But that's early on in the discussion there. It's not necessarily something that this specific project is looking to really hone in on.
Okay, thank you.
Yep.
I don't believe we had another panelist question, but we do have about 2 minutes left in the Q&A. Jim, did you have anything else on your list?
Oh, yes, there was one more about, can you talk a little bit about cybersecurity and how that fits in here?
Yes, so the specifications themselves are built on existing cybersecure standards, mostly off of the OAuth specifications. And so those are the basis that widespread adoption of authentication and connectivity protocols are used. And so we have a fairly robust cybersecurity posture as far as establishing that connectivity, as well as ensuring customer consent where customer consent is needed using that OAuth authorization request flow. And so everything kind of built in is assumed to be confidential information. All of these data exchanges are assumed to be encrypted and confidential by default because they're built on those widespread and stable and mature authorization and connection protocols.
Thank you.
Yep.
All right. Well, I think that was it from our list, Jim. We really appreciate your time. Thank you so much for your presentation. And we appreciate you being here today.
My pleasure. Thank you, everybody.
All right. It looks like we have our next team queued up as well. Alex, do you want to let us know if you can hear us?
Yep, I can hear you. Can you hear me?
Yep, coming through great.
Great. And can we see the slides here now?
Yes.
Okay, excellent. Great. Well, hello, everyone. My name is Alex Farley. I'm the software development manager at Grid Elevated. I'm here today to talk about Midas, the multi-source data acquisition, analysis, and sharing platform. Throughout this project, we've worked with Heber Light and Power. And so to talk about kind of the challenge that Heber Light and Power and utilities in general are facing today, as the energy transition is accelerating, grid transformation is persisting, traditional analysis has become much less effective and accurate than it used to be, especially for these smaller rural utilities like Heber Light and Power. As variable renewable generation, electrification increases, that combines with unprecedented weather events, traditional forecasting and resource management tools have become less accurate than they used to be. And so the main way you can combat this, of course, is integrating more data into your systems. But there can be significant overhead required to actually integrate that data into systems. And so, it's not uncommon for these operators to be navigating a dozen different tabs on a browser, looking at different weather forecasts at different locations, interfacing with X number of APIs and having 4 or 5 spreadsheets open just to be making an hour ahead decision. And when you're a smaller team, that can be technically prohibitive to integrate that into your actual forecasts or models. And then when you combine that with looking at legacy software systems, and when a lot of operational decision making is based off of operator intuition, ultimately you have quite a few utilities operating on the back foot. They're reacting to what's happening in the system rather than proactively planning and dispatching their resources accordingly. So our partner, Heber Light and Power, is running into these issues, and we believe many other utilities are as well. So what we've done to address this is we've developed the Midas platform. So Midas is a cloud-based platform, and it's designed to empower intelligent decision-making by making big data accessible for utilities, and then leveraging that data and turning it into meaningful insights through analytics. So Midas is developed to be accessible to any type of utility in that it can interface with any technology stack. So we have a web-based dashboard, a REST API, and Excel macros. So we can really meet a utility where their current technology stack is. From those interfaces, we also then have our analytic tools. And so we have a load forecasting tool and a resource forecasting tool, both which use AI to make predictions. And then in addition to that, we have a resource optimization and market participation tool. And this is looking at creating day-ahead schedules for dispatchable generation. Of course, all of this is then predicated upon a cybersecure data pipeline, and we're ensuring that utility data is secured and encrypted properly, that it only ever has access to who a utility deems it should have, or deems should have access. And so ultimately, in implementing this platform, the benefits a utility realizes is first, reduce real-time balancing costs. So more accurate forecasts ultimately reduce costs. Similarly, improved day-ahead scheduling can increase savings. And then moreover, more broadly, is improved operator situational awareness. And so now I have a demo to show of the Midas platform in action.
Users can access the Midas platform directly from the browser through a secure login procedure. From here, users can see their real-time dashboard, which aggregates information from over 10,000 sensors, including weather forecasts, California ISO electricity price and demand outlooks, and water flow and elevation information. Users can customize their own dashboard to display whatever information they find most relevant to their operations by selecting specific sensor locations. Users can also securely upload their own private data to the Midas platform through a cybersecure data pipeline. From the library page, users can import any spreadsheet file. Users then must identify which columns will be included in the data upload. After providing annotations, users can select access controls on the data and if it shall be accessible by the Midas analytical tools. This allows the platform to access utility data only if it is approved by the utility user, allowing the platform to function without ongoing connections directly interfacing with critical utility software. This also provides the infrastructure for users to provide more recent training data to update their analytic tools. Users can also run 24-hour load forecasts from the dashboard. They can view previous forecasts run in the last 24 hours. The only inputs required to run a new forecast is the previous 24 hours of load and the forecast hour, which can be entered manually from a file or from an earlier forecast. Once the forecast runs, users can view it here or download the raw data. Users can then use those load forecasts to run the resource optimization and market participation tool. Users must also input initial conditions, which in this case are the starting state of charge of the energy storage, natural gas prices and purchase quantities, and maximum market purchase capacity. From this, users can see their optimal resource dispatch schedule, and market participation strategies. Users can also run day-ahead solar forecasts for specific locations. This model requires irradiance and temperature forecasts, which can be input by the user, or use the NOAA high-resolution rapid refresh model that is already integrated within the platform. Users also have the option to run the Midas analytical tools straight from Excel workbooks. After logging in, users can use macros to run load forecasting, resource optimization and market participation, and solar PV forecasting tools and output their results. Alternatively, savvy users can interface directly with the Midas REST API to access the tools and integrate them directly in their own systems. Users can
Awesome. So talking more about our progress throughout this project, we've been working very closely with Heber Light and Power. We've had dozens of meetings at this point to discuss the data they were providing us, their operations, and their current challenges. From there, with some of the data provided, we first initiated a case study looking at their operations and their forecasts and see how our analytic tools can provide improvements. Now, currently, Heber Light and Power is using the Midas dashboard in parallel to their operations. And so they're evaluating the platform not only at the results of the analytic tools, but see how its ease of use fits into their current operations. When we're looking forward, we really believe we have a straightforward integration into their current operations, given that their two primary interfaces are web-based and Excel. And so we really believe Midas has a seamless integration into their operations. So looking into the actual case study results, so Heber Light and Power's current load forecasting, their hour load forecasting has a 9.6% mean absolute percentage error. We look at the Midas load forecasting accuracy, we have it at below 3%, so a significant improvement there. And even the Midas 24-hour load prediction is a significant improvement from the current hour-ahead load forecasting protocol that's used there. You can see in this figure to the right that the Midas hour-ahead load forecasting is really accurate, especially at the peaks of load, which is especially important in operations. We also see similar improvements in solar PV forecasting. So again, with Heber Light and Power's current day-ahead solar forecasting algorithm, they have about a 708 kilowatt root mean squared error. Midas again significantly improves on this, cutting that error by more than half. And again, we can see that here to the right that the Midas AI-based forecast is much closer to the actual generation profile than the previous tools being used by Heber Light and Power. Then we will also look at the resource optimization market participation tool. And so what we can see here is once we implement this tool, we have a 4.1% reduction in operating costs. And then if we combine this tool with the improved load forecasting, we actually have a 45% reduction in real-time balancing costs. So aggregating these tools together has meaningful results at the utility's bottom line. So looking forward in terms of broader industry impacts, we really believe Midas is primed to be implemented across a number of utilities. We believe this for a multitude of reasons. First, the accessible interfaces are incredibly important. We believe we are able to provide meaningful tools to a smaller utility such as Heber Light and Power or a larger utility, and they can all access it with their current technology stack, given that we have a web dashboard, an Excel integration, and an API. So we're really able to meet a utility where they currently are, which reduces implementation time and ultimately increases adoption. We also have model update infrastructure. So as you saw in the demo, users can upload more recent data to then upload their analytic tools. So ultimately, these tools can continue to have value. And there's already an automated training process. In addition to that, the models have a very lightweight design. So we do not foresee as more users and more utilities ultimately integrate with the Midas platform. We do not foresee our cloud architecture costs increasing correspondingly. And of course, there's a very important security element here in which we have secure account management. We can ensure that, for example, Heber Light and Power's data and their analytic tools will never be used for utility A's analytic tools or their data, unless both of them have an agreement to share data. Great. Thank you. Happy to answer any questions.
Great. Thank you, Alex. Are there any questions from our panelists before we hop to Jim's list? Ming, go ahead.
Hi, hi, Alex. So I assume your solution is probably better for those small utilities who don't have expertise in terms of forecasting and also dispatch, like optimal dispatchment. Have you been, reaching out to more small utilities, trying to gauge their interest? And have you talked to them about how much effort would it be need? And because this is very much data driven, so it will be very, utility specific. You need effort from both sides, you and them. Have you done that?
Yes, that's an excellent question. And yes, we have. So we've been, Heber Light and Power is a member of UAMPS. It's the Utah Associated Municipal Power Systems. It's a group of, I believe, 50 municipal electricity co-ops and power utilities. And so we've been working, of course, with Heber Light and Power, but also with UAMPS as a whole. As you're saying, this is a challenge exhibited by many smaller utilities, and we believe it's important that we address that, and we have to meet them where they are. And so we, working with Heber Light and Power, they already interact with a number of utilities within UAMPS. We are interacting with those utilities as well, and we believe the benefits that we've provided to Heber Light and Power easily can kind of cascade to those other utilities, given that they all have similar, of course, not exactly the same, but similar resource mixes and similar operations. So yes, we are in discussion with other utilities and UAMPS because we believe this has kind of cascading effects.
Thank you.
Great. Let's see. Oh, looks like we have one hand raised.
Yeah, thank you for the presentation. It's really interesting. Can you shed some light on how you are able to achieve higher accuracy from the utilities baseline methods?
Sure. Sure. Yeah. So especially with these smaller utilities, what we found is a lot of their forecasting is predicated on historic data. And so that historic data is largely selected by a forecaster, an operator, resource manager. And what we found and what they're running into is that historic data is less representative for what tomorrow's load would be than it was in years past. And so that has to do with a number of factors, of course, energy transition, the grid's transforming. What we are able to do is with our AI-based methods, of course, we leverage that external data, but we're also able to consider other external factors. So for example, we're able to look at weather forecasts, historic weather forecasts, and we're able to kind of identify some of those patterns in load forecasting that traditionally just looking at previous, whether it's yesterday's or what this day last year's load cannot simply identify.
Thank you.
There is one question that a reviewer asked that I think actually follows on the first question that you got. While he first question kind of made the assumption that you were targeting smaller organizations. Is that the case where there's tools out there from big organizations that do unit commitment, but is that the niche that you're not? Are you trying to compete with those big organizations and have new features that they don't have? Or are you saying our unit commitment here is targeting a different type of organization? That makes sense?
Yeah. So I'd certainly say the smaller customers, so those rural utilities, are our beachhead market. I wouldn't say we necessarily want to be, we completely envision limiting ourselves there, but we see the greatest, I guess, customer pains and the lowest hanging fruit in integrating some of these tools, and we can have kind of the greatest impacts, the greatest savings. These larger utilities, they might already have, as you mentioned, they might already have a data analytics team in which they have the bandwidth to be addressing some of these. And we don't want to necessarily discount our work and say we can't provide improvements, but we certainly see the greatest opportunity for improvements with these smaller utilities.
Great, thanks. And Carly, with 20 minutes left, that was it for the questions that have been submitted. So with 20 minutes left, might be
Sure.
good transition. Thank you, guys.
Thank you.
Appreciate it. Thank you so much for your time, Alex. All right, I believe we just have one final team. If there were any additional questions, if there were for Alex, feel free to email them over to us and we'll make sure that we share those. But let's get the next team transitioned in. All right, we should have both of them on the line now. You guys could let us know if you can hear us now that you're panelists.
Hello, yes, I'm here. And we are two panelists, Divi Guel as well from our company.
Big thanks so much for joining us today. Feel free to start whenever.
All right, I'm sharing my screen. And full mode. Do you see it?
Yes.
All right. Hello, my name is Vitalina Ivanova. I am a CTO and co-founder of Coinformatics. Together with our lead engineer, Divian Guel, we're going to present to you our progress through the first phase of this competition. We are working on early alert system decision support tool for energy utilities in partnership with Excel Energy. The challenge, which is presented currently to the energy industry, it's a grand one. The climate change triggers a lot of extreme events such as heat waves, wildfires, freezes, and the list is endless, but those are costing a lot of electrical grid failures, economic losses, losses of lives, unstable electricity rates. Some of the most devastating fires nationwide were caused by utility grid failure. The fire in Paradise wiped the whole town for overnight, caused by electricity failure from the PG&E in California, 2018. Last year, we had similar devastation in Hawaii, caused also by energy utility Hawaiian electricity. And this last year, our partner, Excel Energy, is liable for the Smokehouse Creek fire in Texas. What we can do better, how we can prevent such disasters to happen in the future, and how you winterize your operations when we have such a large range of extremes. Do you prepare for Texas freeze, like the one in the winter of 2021? There was a storm freeze overall, the entire Texas. Or you have to prepare and get ready for another record-breaking fire like the last winter, 2024, also in Texas, the Smokehouse Creek mega fire. And this is where our solution can help. A concept is to build resilience through accurate seasonal prediction. We offer up to 1 year ahead localized, highly accurate climate predictions. And the unique offering is predicting extreme events with lead time of 1 year. We're building a platform which combines physical models like climate models, weather models, historical observations, together with AI technology. We're producing forecast in the near-term range, which is not covered currently by the weather industry or the future long-term projections in the climate modeling community. So our predictions can give you a lead time of 1 month to 1 year ahead, and that will be a good period where the utilities can prepare proactively for the climate risks and disasters they can face. In response to our partner, we developed the use case of our solution for the Texas smokehouse fire, which burned more than 1 million acres of area wild forest, and also near to some villages, and cost about 250 million in viability for our Xcel Energy partner. We presented forecasts produced 3 months ahead of the fire event, and what we showed and demonstrated to our partner was that our forecast solutions can capture extreme events, such as the smokehouse fire event, where we had extremely high temperatures, almost like a heat wave for a winter type conditions, very dry humidity conditions which dry the vegetations, and gust winds which caused the ignition of the fire in the end. So this 3 months lead time period could be a good time of building a better mitigation strategy. During the first phase of the competition, our plan was, and we acquired new data sets. For example, the remote automatic weather stations, which are strategically located in the forest and remote areas where normal public data sets are not covering. We also implemented fire danger metrics based on the US National Fire Danger System. We are working with California Firefighter Organization, the US Forest Service to build the proper metrics and have a better accurate prediction of fire danger. We also developed and demonstrated to our partner user-friendly dashboards which feature fire danger and heat waves analytics and risk exposure alerts. And with that, I will give Vivian the opportunity to demonstrate our current development.
Sure. Okay. Let's see if this works. Great. Okay, so I'm walking you through our energy alert system dashboard, which is built on top of our forecast. The validations which you did for the Xcel Energy use case, they were for the smokehouse fire conditions, and this is where the first smokehouse fire happened in its spread area. To use the dashboard, you can select the weather station that you're interested in. You can select the time region that you're interested in, and you press refresh, and you get some values. So the analytics here, they built on top of the forecast. What we are forecasting here is the heat stress index and the fire weather index. We are expanding the scope of our localized forecast to a 4-kilometer grid, which would in future cover the entire US. And this is what the representation of those modified dashboards will look like. Sorry.
Back to my presentation slides. So the solutions which we provide, we're building on the Google Cloud, and we easily integrate through API toolkits that forecast in the utility tools such as Encompass, Promote, or Plexus, or the utility operators can access and monitor the early alert system through the user interface. And of course, all of that information can give the utility decision maker plenty of time to build a robust strategy to mitigate any climate risk ahead of time. What is the impact of our solution? So looking at our Xcel Energy's partner community, it serves more than 3.4 million customers over 8 states in the US. Only last year, the Xcel acquired more than 200 million in financial liabilities, and that's with the cost of community suffering from wildfires or power outages. Working with our solution can improve the utilities and community customers' climate awareness. It will provide proactive risk mitigation capability, which will optimize grid operation, maintenance schedules to prevent and prepare the vulnerable structures. It will reduce the financial liabilities and stabilize the electricity rates. It can improve financial contracts, which are quarterly or annually, knowing this information ahead of time. And importantly, let's say it can safeguard communities and environment. We believe our solution can help to build resilience, and we are looking forward towards the next steps of developing it. And with that, we want to thank our network, to thank you for your support. And I'll finish with our slide, which you probably know from the application, and open for questions.
Great, thank you so much. We'll go ahead and open it up to our panelists before we hop over to Jim.
Should I stop sharing or?
You can leave your screen sharing if you'd like.
All right.
Andrew,
Okay.
go ahead.
All right, thanks for the presentation. So I have actually a few questions to save time. The first is, anyone like us, we do long-term forecasting. We know the future, the uncertainties or standard deviation grows with respect to time. So the future is really, we call the cone. So are you providing a point forecast in the future, or like you claim 95% accurate, is that like 95% confidence interval, or what do you exactly provide?
Good question. Yes, our forecasts are probabilistic. So at any record of time, it's a probabilistic distribution, and it's important to have it because these extremes are in the tails of the distribution. I can actually go back and show. So, sorry. So yeah, in orange or any color here, that's our forecast, and those are percentiles, every 10 percentile from 0 to 100, and they show a distribution in any of the future moments.
Yeah. Okay. Yeah, my other question is, so in your validation, so you look at the past event in Texas. So basically you know exactly where the wildfire happened, but now you're predicting something in the future. How big of the geographic area you need to cover, like, and how can you have the capability to go through that, for example, vast data, like covering really remote areas to identify where the potential areas gonna have troubles? How are you able to do that?
Well, we are scaling up. So yes, the test case, we built it on 4 points, which were in the area of the burned area from the fire. But moving forward, we are scaling up to a gridded product, which will have a resolution of 4 kilometers, or we can even go down that if resources allow. And I believe in that type of high resolution gridded product, we can see the potential areas which are vulnerable and focus there our attention.
No, I know, but my question is really, do you have the, like, what computation power or resources need to run that finer detail, but then
Right.
cover a large area of geographically?
Right. So we got Google Cloud credits for quite a bit of amount, which we are going currently to evaluate exactly what are the needs and the scales we can go. We also had earlier testing early forecasts ahead of time, also with 1 year ahead of time. That actually is much heavier computational load. So currently we are focusing on the spatial resolution. So yes, that's still in a testing process. We just got the credits, and hopefully that will help us to make that accurate evaluation. Of course, it needs to be done.
Thank you.
Looks like we had one more hand raised.
Yeah, hey. So, so one question is that, what will be the next step? So how do we use this information by the utility? I mean, is it going to also map their assets on these?
Yes, that's the plan. So the plan is to inquire from the utility the map of their assets, the map of their user communities and the most vulnerable communities, and integrate that in a risk type of score, which can give you where the risk is the highest and when it's going to happen. Yes, that's in the plan of our work for moving forward.
Okay, thank you.
Fernando, go ahead. Fernando, did you have a question?
Sorry, I was talking to mute. So, so in this slide, you're showing like, heat wave, gust, and dry, and it was able to predict that. But have you seen any other locations where you see the same kind of like, measurements, and it like, you don't have that kind of like, fire issue, or it's like a false positive? Have you tested that out?
So this heat wave is really unique. I think that was the real reason that it triggered the fire. But earlier that year, we analyzed earlier periods as well. There was high gust and dry conditions, which probably prepared the vegetation in that area to be ready to burn as a dead fuel. But the temperatures were lower. And actually, the high gust at that period was raising the fire danger. But it's really difficult to predict the ignition. In this case, it was the heat wave triggering it. We had validated our solutions also in California, and generally these fire weather predictions can only raise your attention. They're not going to be able to predict exactly if there will be ignition. The ignition is separate. You only have to check the utility in that area if the structure is compromised, if there is any hanging line or pole is broken. So that's really what this is bringing attention in specific areas where will be a fire danger present.
Oh, okay, thank you.
Thanks, Fernando. Jim, I think we have time for about one more question if you happen to have any that weren't addressed by the panel.
There was sort of, I'll try to summarize a couple of things that came up with, so the Smokehouse Creek fire caused by a broken pole and downed lines, right, that happened to correspond with that heat wave and dry
Right.
conditions. But if that pole had been hit and broken, 2 weeks earlier, how then do you have a sense for, there's just such an interplay between not only the climate and the weather, but also what's happening on the grid with lines hitting the ground, that which can't be predicted, right? So can you just talk through that? And again, I think this gets at how utilities would use it. And also, during that heat wave, again, what should what should they have done? I mean, de-energize lines over a huge region. So can you just talk a little bit more about how there's that human impact of things getting knocked over and touching the ground that doesn't have to do with weather? How does that get integrated and here?
Well, I believe the gust winds should definitely be alerting you about your structure, and definitely putting sensors on your poles or lines will help to register those type of events. We are working with a partner who are providing sensors to the utilities, putting them in every pole, and they register events of high gust or high temperatures, and generally have information for the equipment monitored all the time. So I believe that together with the environmental type of conditions can help integrate and optimize the decisions to make. But if we have a very localized danger forecast, I believe just checking that area for any structural or even equipment being old and needing a maintenance, maybe you need to maintain more often, or having that information that that area will be under danger, go and check that type of structural vulnerabilities. And the vegetation around. So in this case, it was really these unusual winter conditions, either by natural or climate change type of trends, where the vegetation was already dead by the time this next heat wave hit, and the gust winds together with the gust winds increased the danger for fire ignition. That will be a continuous conversation with the utility partner to understand how best our information can help. And that's the plan to continue working on in this project.
Thank you.
Great. Thank you so much for that clarification. Looks like we are right at time, and you're actually our last team to present today. So I just want to thank you all for joining, for all of the presentations, everyone that presented. I did drop a link in the chat. Just as a reminder, this was recorded, so it will become available on HeroX within the next couple days. If there were any additional questions, feel free to shoot them our way or start a message in the forum. But we really appreciate you all being here, especially our judges and panelists. Your time is so appreciated, and thank you so much for joining. Have a great day.
Thank you. Thank you.
Thank you.